Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Find a comfortable position and gently lower the brightness of your screen. There's nothing you need to do now. Nothing to learn or remember. Tonight, we'll drift through the quiet cosmos, exploring its gentlest truths. The universe is a place of immense scale and profound silence. But it isn't empty. It's filled with a soft, steady rhythm. A quiet dance of gravity and light that has unfolded for billions of years. As we begin our journey, allow your body to grow heavy, your breath to find its own easy pace. If your mind wanders, just let it. These words aren't here to be held onto. They're simply sounds to fill the space, like the gentle hum of a distant star. If you fall asleep, that's why we are here. Let these facts be the soft, steady rhythm that guides you toward rest. Our journey begins now, in the vast, peaceful darkness between the stars. Before we drift too far, if you enjoy these calm explorations of the cosmos, you're welcome to subscribe. It helps others find their way to this quiet corner of the universe. For now, though, just settle in and let go. The universe is waiting. The fabric of our cosmic home. Let's begin with the foundations of our cosmic home. As you lie here, the world outside seems still. But our planet is in constant, gentle motion. Earth spins on its axis once every 24 hours, turning as slowly to face different parts of the night sky. And as it orbits the sun each year, our view of the constellations shifts with the seasons. All this movement happens so smoothly, so reliably, that we feel only stillness. To measure the incredible distances in space, astronomers use a unit called a light year. A light year is the distance light travels in 1 year. About 9.5 trillion kilometers. It isn't a measure of time, but of vast, quiet distance. When we look at the stars, we're looking into the past, because light takes time to reach us. The starlight you see tonight left its star many years ago. The light from our own sun takes about 8 minutes to reach us. For the nearest star system, it's over 4 years. And for distant galaxies, we're seeing light that's billions of years old. Some of the stars we admire in our night sky may have already faded away, but their light continues its long, peaceful journey across the void, a steady whisper from the past. Gravity is the gentle force that orchestrates the universe. But it isn't a pull in the way we often think. Albert Einstein realized that massive objects, like stars and planets, actually curve the very fabric of space and time around them. Planets orbit the sun not because they're being pulled, but because they are following the straightest possible path through this curved space-time. Like a marble rolling around the edge of a gentle slope. This curvature of space-time is what we feel as gravity. It's a quiet, persistent force that holds galaxies together, keeps planets in their orbits, and holds you softly in your bed. Our solar neighborhood. Now, let's draw our focus a little closer to the calm and familiar neighborhood of our solar system. At the center is the Sun, a star so large that it contains 99.8% of all the mass in our entire solar system. It's a peaceful, middle-aged star, and has been burning steadily for about 4.6 billion years. It rotates on its axis, but much slower than Earth, taking about 25 to 30 days to complete one turn. The Sun isn't perfectly round. Because it spins, it bulges slightly at its equator. It also loses an incredible amount of mass every second as it converts matter into energy. But it's so massive that this is like a gentle sigh. And it has more than enough fuel to continue shining for another 5 billion years. Let's drift to the planets closest to the Sun. Mercury and Venus are the only two planets in our solar system with no moons. They travel alone in their orbits. Mercury is the closest planet to the Sun, yet even on its scorching surface, there are craters at its poles that stay in permanent shadow, cold enough to hold ice. Venus is a world of contrasts. It spins backward compared to most other planets. So on Venus, the Sun would appear to rise in the west and set in the east. A day on Venus is actually longer than its year. It takes 243 Earth days to spin once on its axis, but only 225 Earth days to orbit the Sun. Our own planet, Earth, is the only place we know of with liquid water on its surface, and an atmosphere with that perfect balance of nitrogen and oxygen for life as we know it. Earth is also the only planet in our solar system with active plate tectonics. Its crust is broken into massive plates that float on the molten interior, a process that recycles elements and keeps our planet geologically alive and comfortable. Our beautiful moon doesn't produce its own light. It shines simply by reflecting the light of the Sun. We also only ever see one side of it. This is because the moon rotates on its axis in the exact same amount of time it takes to orbit the Earth. The moon isn't perfectly round. It's slightly lemon-shaped, with flattened poles and bulges at its equator. This unique shape is thought to be a result of Earth's gravitational pull when the moon was first formed. And it is slowly, very slowly, drifting away from us, at a rate of about 3.8 centimeters per year. Billions of years from now, it will be much farther away than it is tonight. Mars, the red planet, has days that are very similar to Earth's, just about 40 minutes longer. These Martian days are called sols. Sunsets on Mars aren't red, but blue. The fine dust in its thin atmosphere scatters red light away, allowing blue light to penetrate more directly when the Sun is on the horizon. Between Mars and Jupiter lies the main asteroid belt, a region filled with millions of rocky objects. These asteroids aren't crowded together. They're typically hundreds of thousands of kilometers apart. They are the leftover building blocks from the solar system's formation, ancient rocks that never quite came together to form a planet. Jupiter is the giant of our solar system. It's so large that all the other planets could fit inside it. As of early 2026, we know Jupiter has 101 confirmed moons. Its largest, Ganymede, is bigger than the planet Mercury. Another of Jupiter's moons, Europa, is believed to have a vast liquid water ocean beneath its icy shell, containing more water than all of Earth's oceans combined. Saturn is famous for its stunning rings. But these rings aren't solid. They're made of billions of small particles of ice and rock, ranging in size from a speck of dust to the size of a house. Surprisingly, the rings are incredibly thin, only about 10 meters thick in most places. And they are relatively young, likely forming after the dinosaurs had already disappeared from Earth. Uranus and Neptune are known as the ice giants. They aren't gas giants like Jupiter and Saturn. They're composed of heavier elements, with atmospheres of hydrogen, helium, and methane. It's that methane that gives them their beautiful blue and turquoise colors. As it absorbs red light from the Sun, Uranus is tilted on its side, likely due to a massive collision in its distant past. This extreme tilt means that a day at its north pole can last for 42 continuous years of sunlight, followed by 42 years of darkness. Neptune is the most distant planet from the Sun, and it takes nearly 165 Earth years to complete just one orbit. Since its discovery in 1846, it has completed only one full journey around the Sun. One of its moons, Triton, orbits the planet backwards, against the direction of Neptune's rotation. Beyond Neptune lies the Kuiper Belt, a vast, icy region home to dwarf planets like Pluto. And even further out is the theoretical Oort cloud, a giant, spherical shell of icy bodies thought to surround our entire solar system. A quiet, frozen frontier. The life of stars. Now, let's drift away from our local neighborhood and turn our attention to the stars themselves. These quiet lights in the night sky aren't just static points. They're dynamic, living things with their own life cycles. Every star you can see with your unaided eye is bigger and brighter than our Sun. The vast majority of stars are too small and dim to be seen from so far away. Stars are born inside vast, cold clouds of gas and dust called nebulae. These stellar nurseries are some of the most beautiful objects in the cosmos. Over millions of years, gravity gently pulls clumps of gas and dust together. As the material gets denser, it heats up. And when the core becomes hot enough, nuclear fusion begins. A star is born and begins to shine. The color of a star tells us its temperature. The hottest stars are blue, burning at tens of thousands of degrees. The coolest stars are red. Yellow stars, like our Sun, are in between. Interestingly, there are no green stars. While stars do emit green light, our eyes mix the colors in a way that makes them appear white or bluish-white. The most common type of star in the universe is the red dwarf. These stars are small, cool, and incredibly long-lived. They burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. This means that not a single red dwarf has ever reached old age yet. The universe is still too young. Massive stars, on the other hand, live fast and die young. Blue giants, which can be millions of times brighter than our Sun, burn through their fuel in just a few million years. Their lives are brief but spectacular. Our own Sun has a quiet future planned. In about 5 billion years, it will run out of hydrogen in its core. It will then swell into a red giant, its outer layers expanding so much they may engulf the inner planets, possibly even Earth. After this phase, the Sun will gently shed its outer layers, creating a beautiful, glowing cloud called a planetary nebula. The remaining core will shrink into a dense, hot white dwarf, which will then slowly cool and fade over billions of more years. When a truly massive star runs out of fuel, its end is far more dramatic. Its core collapses under its own gravity, and the star explodes in a cataclysmic event called a supernova. For a brief period, a supernova can outshine an entire galaxy. These explosions aren't just endings. They're also beginnings. Supernovae scatter heavy elements, like carbon, oxygen, and iron, across space. These elements enrich the cosmic clouds, providing the raw materials for new stars, new planets, and eventually, life. Almost every atom in your body was forged inside a star that lived and died long ago. Sometimes, the core of an exploding massive star doesn't become a white dwarf. It collapses further into an incredibly dense object called a neutron star. A neutron star is so dense that a single teaspoon of its material would weigh 1 billion tons. Some neutron stars spin hundreds of times per second, sweeping beams of radiation through space like a cosmic lighthouse. We call these pulsars. But for the most massive stars of all, there is an even stranger fate. When they die, their core collapses so completely that nothing can stop it. Gravity becomes so strong that it creates a region of space-time from which nothing, not even light, can escape. This is a black hole. However, not all massive stars explode in a bright supernova. The most massive ones can sometimes collapse directly into a black hole with no visible explosion at all. The star simply disappears. A quiet, sudden end. Many stars aren't alone. They exist in pairs or groups, orbiting a common center of gravity. These are called binary or multiple star systems. By watching these stellar dances, astronomers can learn about a star's mass and evolution. Our own sun is a little unusual in that it travels through the galaxy alone. On a grander scale, stars are gathered into enormous, ancient collections called globular clusters. These are dense, spherical swarms of hundreds of thousands of old stars, orbiting the edges of our galaxy like silent, glittering satellites. Many of these clusters are over 12 billion years old, making them fossils from the very early universe. The light from the stars doesn't truly twinkle. That twinkling effect is caused by Earth's atmosphere. As starlight passes through the turbulent layers of air, it gets bent and distorted, causing its brightness and position to appear to shift from moment to moment. Above the atmosphere, in the silence of space, the stars shine with a steady, unwavering light. The realm of galaxies. Let's zoom out even further now, into the realm of the galaxies. These are immense islands of stars, gas, and dust, drifting through the cosmic ocean. Our home galaxy is the Milky Way. It's a spiral galaxy, more than 100,000 light-years across. It contains hundreds of billions of stars, and our solar system is nestled in one of its spiral arms, about halfway from the galactic center. Our entire solar system orbits the center of the Milky Way. It takes about 230 million years to complete a single orbit. This means the last time Earth was in this position, dinosaurs were just beginning to appear. From our perspective here on Earth, the Milky Way appears as a faint, milky band of light stretching across the night sky. This band is actually the light from billions of distant stars in the galaxy's disk, all seen edge-on. At the very center of our Milky Way, and most other large galaxies, lies a supermassive black hole. Ours is named Sagittarius A star. It has a mass of about 4 million times that of our Sun, yet stars orbit it peacefully, held in its immense gravitational field. Galaxies come in many shapes and sizes.
Besides spirals like our own, there are elliptical galaxies, which are smooth, oval-shaped collections of older stars. And there are irregular galaxies, which have no defined shape at all. The smallest galaxies, called dwarf galaxies, may contain only a few thousand stars. The largest can hold trillions of stars and span over 1 million light-years. Galaxies aren't scattered randomly through space. Gravity draws them together into groups and clusters. The Milky Way is part of a small gathering of over 50 galaxies called the Local Group. Our nearest large galactic neighbor is the Andromeda Galaxy, which is about 2.5 million light-years away. Andromeda is currently moving toward our Milky Way, and in about 4 to 5 billion years, the two galaxies will begin a long, slow process of merging. This won't be a violent collision of stars, because the space between stars is just so vast. Instead, the two galaxies will dance around each other for billions of years, their gravity slowly weaving them together into one single, larger galaxy. Galaxy clusters can contain thousands of galaxies, all bound together by gravity. The space between the galaxies in a cluster isn't empty. It's filled with a vast cloud of hot gas that glows faintly in X-ray light. On the largest scales, galaxies and galaxy clusters are arranged in a vast, intricate structure known as the cosmic web. This web is made of long filaments of galaxies surrounding enormous, nearly empty regions called cosmic voids. These voids can be millions of light years across. Vast expanses of quiet emptiness. The universe, viewed from afar, looks like a delicate, glowing network. A tapestry of light and darkness. The light from the most distant galaxies has been traveling for over 13 billion years to reach us. When we look at them, we're seeing the universe as it was in its infancy. A time when the very first stars and galaxies were just beginning to form. Because the universe is expanding, the space between galaxies is stretching. This also affects the light traveling through it, causing its wavelength to lengthen and shift toward the red end of the spectrum. This redshift allows astronomers to measure a galaxy's distance and how fast it's moving away from us. Some distant galaxies are receding from us so fast, due to the expansion of space itself, that they appear to be moving away at a rate faster than the speed of light. This doesn't violate physics, because it's the fabric of spacetime itself that is expanding. It simply means their light will never reach us. They have passed beyond our cosmic horizon forever. There are also ghostly galaxies that glow without many stars inside. These are faint, diffuse systems made mostly of gas and dark matter. They are like quiet shadows in the cosmos, challenging our understanding of how galaxies form and grow. The deepest mysteries. As we drift closer to sleep, let's contemplate some of the deepest, most peaceful mysteries of the cosmos. These are the questions that remind us how much we still have to learn, and how wonderful it is to simply wonder. The vast majority of the universe is made of things we can't see. About 27% of the cosmos is dark matter. We know it exists because we can see its gravitational effects on stars and galaxies. Without it, galaxies would fly apart. Dark matter streams silently through the universe, through our galaxy, through our planet, and even through you. Right now, as you rest, it doesn't interact with light or ordinary matter, so it remains completely invisible. Even more mysterious is dark energy, which makes up about 68% of the universe. It's a strange, repulsive force that's causing the expansion of the universe to accelerate. We don't know what dark energy is, only that it's gently but relentlessly pushing everything apart. The ultimate fate of the universe, whether it will expand forever or something else, depends on the true nature of this invisible energy. Let's consider black holes again. A black hole has a boundary called the event horizon. This isn't a physical surface, but a point of no return. Once anything crosses it, it can't escape the black hole's gravity. Time behaves strangely near a black hole. Due to the extreme curvature of space-time, time itself slows down for an observer closer to the event horizon. This effect is called gravitational time dilation. It means that time isn't absolute. It flows at different rates in different parts of the universe. Even here on Earth, a clock on a mountaintop runs ever so slightly faster than a clock at sea level, because it is farther from Earth's center of gravity. When two black holes spiral into each other and merge, they release enormous energy in the form of gravitational waves. These are ripples in the fabric of spacetime itself that travel outward at the speed of light. The first detection of these waves in 2015 was a monumental achievement, confirming a century-old prediction by Einstein. These waves are incredibly faint by the time they reach us, stretching and compressing space by less than the width of an atom. Listening to them allows us to hear the silent songs of the most powerful events in the cosmos. The universe has a faint afterglow from its birth, called the cosmic microwave background radiation. This is the oldest light in the universe, released when the cosmos was just 380,000 years old. It comes from every direction in the sky, a near uniform, gentle hum of microwave energy, the quiet echo of creation. What we can see of the universe is limited. Because the universe has a finite age, there's a boundary to what we can observe, called the cosmic horizon. Light from galaxies beyond this horizon has not yet had enough time to reach us. This doesn't mean the universe ends there. There could be infinitely more universe beyond what we can see. But it is, for now, forever hidden from our view. Even empty space isn't truly empty. According to quantum physics, the vacuum of space is fizzing with tiny, fleeting fluctuations. Pairs of virtual particles blink into and out of existence in moments too brief to measure. This quantum foam is the restless background energy of reality itself. The universe appears to have begun in a state of incredible simplicity and order, and has been slowly moving towards disorder ever since. This principle is known as entropy. In the far, far future, trillions of years from now, all the stars will have burned out, all the black holes will have evaporated, and the universe may reach a final state of maximum entropy, known as heat death. It would be a cold, dark, and uniform state, a final, peaceful silence. But that future is unimaginably distant. For now, we live in the universe's brilliant, vibrant youth, a time of glowing stars, swirling galaxies, and profound mystery. A time for quiet contemplation and for deep, restful sleep. The universe continues its slow, silent dance, whether we're awake to see it or not. The stars continue to trace their ancient paths. Galaxies continue their slow, graceful spirals through the void. Light continues its long journey across billions of years, carrying stories of a time long past. You are a part of this cosmic dance. The atoms in your body were forged in the hearts of stars, and the ground beneath you is a piece of a planet that has been circling its sun for billions of years. As you drift off, feel your connection to this vast, quiet cosmos. You aren't separate from it. You're a way for the universe to know itself. There's no need to think anymore. There's nothing to hold on to. Let the words fade, becoming just shapes of sound. Let the silence of space fill your mind. Let the gentle rhythm of the cosmos guide you into deep, peaceful rest. Part 2: Earth's quiet place in space. Before we drift farther into the universe, it helps to begin with something very close and very easy to forget. Right now, as you rest, your body may feel still. The room may feel still. The night outside may feel still. But Earth is not still at all. It is turning, circling, tilting, gliding, and carrying everything you know along with it through space. And somehow, in the middle of all that motion, it gives us the feeling of steadiness. A floor beneath our feet. A horizon that seems patient. A sky that rises and darkens in a rhythm so familiar that we stop noticing how extraordinary it really is. In this next part of our journey, we stay close to home. We are not going to rush outward to distant galaxies just yet. Instead, we are going to look gently at Earth itself, at where it sits, how it moves, why the sky looks the way it does, why the seasons change, why sunsets glow warm, and why this small world feels so perfectly suited to life. The deeper you look, the stranger and quieter it becomes. Earth is not just the place where we live. It is a tiny moving island, floating through a vast dark sea, wrapped in a thin layer of air and light. If you have ever looked up at the stars and felt that space must be still, that feeling makes sense. Space seems calm from a distance. But our planet is in motion all the time. Earth spins on its axis once every 24 hours. At the same time, it travels around the sun once every year. And the whole solar system is also moving through the Milky Way. We are not parked in one place. We are passengers on a world that never stops moving. And yet, we do not feel any of that motion directly. You do not feel Earth turning beneath you tonight. You do not feel its path around the sun. You do not feel the solar system gliding through the galaxy. The reason is simple and almost comforting. Motion by itself is not what we notice most. What we notice is change in motion. We notice a jolt, a sudden turn, a sharp stop. Earth's movement is so smooth, so steady, that everything on it moves together. The ground, the oceans, the air, the trees, the cities, and you. There is no sudden shove to announce it. There is only quiet continuity. You can think of it the way you might think of a very smooth airplane flight. If the ride is calm, you can forget you are moving at all. Only when turbulence arrives does motion become obvious. Earth offers us a ride so stable that for most of human history, it seemed reasonable to believe the world was standing still and everything else moved around us. One of the most gentle proofs that Earth is rotating is the simple arrival of morning. Day and night are not caused by the sun circling our world. They come from Earth turning slowly, bringing different regions into sunlight and then back into darkness. A full rotation takes about 24 hours, which means that what feels to us like the daily rise and fall of the sun is really our own turning. Sunrise is not the sun climbing. It is your part of Earth rotating into the light. There is something peaceful in that thought. Dawn is not an event happening only above you. It is part of a global rhythm. Somewhere, while one city is settling into darkness, another is receiving its first pale blue light. Somewhere, morning birds are beginning. Somewhere else, evening windows are glowing. The world is turning all the time, carrying each place through the same cycle, over and over, with astonishing consistency. That turning also explains why the stars seem to move across the night sky. If you watch carefully over several hours, constellations shift from east to west. They seem to travel. But once again, what you are mostly seeing is Earth's movement. We are the ones rotating beneath the stars, and the sky appears to move because our point of view is changing. Much of astronomy begins with that humble realization. The universe does not always behave the way it first appears. Earth's other great motion is its journey around the sun. Our planet takes about 365 days to complete one orbit. It travels at an enormous speed, roughly 30 kilometers every second, and still we never feel it. That is one of the strangest truths about everyday life. Even when you are sitting quietly in bed, or listening with your eyes half closed, you are on a world racing around a star. But Earth does not simply orbit the sun in a flat, neat, perfectly upright way. It is tilted. Its axis leans by about 23.5 degrees. That tilt is the reason the seasons exist. Many people grow up with the vague idea that summer happens because Earth is closer to the sun, and winter happens because it is farther away. It sounds reasonable, but it is not the real reason. In fact, Earth is slightly closer to the sun in early January than it is in early July. The seasons come from angle, not distance. Because Earth is tilted, different parts of the planet receive different amounts of direct sunlight at different times of year. When your hemisphere is tilted toward the sunlight arrives more directly, days are longer, and the world tends to warm. That is summer. When your hemisphere tilts away, sunlight strikes at a lower angle, days are shorter, and the world cools. That is winter. Spring and autumn are the quieter in-between moments, when the balance shifts. There is something lovely about that arrangement. The seasons are not signs that Earth has wandered wildly closer or farther from its star. They are the result of a steady lean, held through space as our planet travels its yearly path. Summer is not a rush toward the sun. It is your side of Earth turning its face a little more fully toward the light. And because of that tilt, the planet is always living in contrast. When it is summer in the north, it is winter in the south. When one half of the world is leaning in, the other is leaning away. This means the Earth is never having one single season. It is always holding opposites at once. Autumn leaves in one hemisphere. Spring blossoms in the other. Warm beaches somewhere. Snowfall somewhere else. A planet in balance, but not sameness. The sky itself also carries quiet clues about where we are. During the day, it looks blue, so familiar that it hardly seems worth questioning. But it is worth questioning, because the answer is beautiful. Sunlight looks white to our eyes, yet it contains many colors. As that light enters Earth's atmosphere, it collides with tiny molecules in the air. The shorter blue wavelengths scatter more easily in all directions, which is why blue light gets spread across the sky above us. So when you look upward on a clear day, you are not really seeing a blue dome. You are seeing sunlight scattered by the atmosphere of your own planet. The sky is blue because Earth has air, and because light does not travel through that air unchanged. A blue sky is not just a visual background. It is evidence of a world wrapped in gas and touched by a nearby star. Then evening comes, and the colors change. Sunsets often glow orange, gold, pink, and red. The reason is gentle and precise. When the sun sits low on the horizon, its light must pass through more of Earth's atmosphere before reaching your eyes. Along that longer path, much of the blue light is scattered away. The warmer colors remain more strongly, and the sky begins to soften into amber and rose. That is why sunset feels different from noon, even before the temperature changes. The world is literally being filtered through a longer corridor of air. The light becomes older, lower, softer. It has traveled farther through the atmosphere. Evening is not just the end of day. It is sunlight seen through more of Earth. Twilight, too, has its own quiet science. Even after the sun drops below the horizon, the sky does not turn black at once. Some sunlight is still being scattered high in the atmosphere, keeping the world faintly lit for a while longer. The day leaves slowly. It lingers in the upper air before it is gone. That in-between light, neither full day nor full night, belongs to the geometry of Earth and Sun and atmosphere. It is one more reminder that our planet lives inside layered transitions, not sharp edges. If we step back a little farther, Earth begins to look very small. The planet feels large to us because we live on it. Oceans seem vast. Continents seem permanent. But in the scale of the solar system, Earth is tiny. The Sun contains almost all the mass in the solar system. Earth is only one small world among several, and even among rocky planets it is modest in size. If the Sun were imagined as a large object in a room, Earth would be something much smaller and much farther away than instinct suggests. And yet small does not mean unimportant. In fact, one of the most humbling facts in science is that everything familiar to human life has happened on a world that would be almost invisible from far enough away. Every language, every song, every war, every love letter, every city at dawn, every child learning to read, every person staring into the night sky and wondering what it all means, all of it has unfolded on this narrow skin of rock, water, and air. That air matters more than we tend to notice. Earth's atmosphere is thin compared with the size of the planet. If Earth were reduced to the size of a common globe, the breathable layer would be almost like a delicate coating. Yet within that thin layer lives weather, sound, breath, cloud, rain, and the blue of day. It is made mostly of nitrogen, with oxygen making up a smaller but vital share, along with traces of other gases. It is not a thick wall. It is a fragile envelope. And this envelope does many jobs at once. It gives us air to breathe. It helps regulate temperature. It carries water vapor that can become clouds and rain. It scatters sunlight into the blue sky. It softens incoming radiation. It burns up many small meteoroids before they reach the ground. It lets the planet be alive in a way a bare rock in space cannot be. Without an atmosphere, Earth would be harsher and quieter in ways that are difficult to imagine. The sky would be black even in daytime. There would be no drifting clouds, no blue noon, no red sunset in the form we know. Sound would not travel through empty space the way it moves through air, so the world around you would be far more silent. Breathing would be impossible. Temperature differences between light and dark would become much more extreme. What we think of as normal life depends on this thin layer more than most of us ever stop to consider. Earth is also protected by something we cannot see directly. Deep beneath the surface, the motion of molten metal in the outer core helps create a magnetic field around the planet. This field extends outward into space and helps deflect many charged particles streaming from the sun. Without that shield, solar radiation would be a greater threat to the atmosphere and to life at the surface. So even the hidden interior of Earth is part of what makes the outer world gentle enough for us to exist. Then there is water, perhaps the quietest miracle of all. Earth is the only world we know for certain where liquid water flows openly across the surface in great abundance. Not just frozen at the poles, not just hidden in rock, but moving in oceans, rivers, rain, clouds, mist, and dew. Water stores heat, shapes climate, feeds weather, carves land, and allows chemistry to become life. A sleeping planet of stone is one thing. A world where water moves is another. Earth's location helps make that possible. Our planet sits in the region around the sun where temperatures can allow liquid water to exist on the surface. People often call this the habitable zone, though the phrase can sound more certain than reality really is. Being in the right zone is not enough on its own. A planet also needs the right atmosphere, the right chemistry, long periods of stability, and probably a good measure of luck. Still, Earth appears to occupy a rare and fortunate balance. Not too close, not too far. Warm enough for oceans, cool enough for clouds, steady enough for life to persist. And that steadiness may be one of the most extraordinary things about Earth. We often think of habitability as though it is a switch that turns on, but it is more like a long, delicate balance held over immense stretches of time. The sun has remained stable enough. Earth has kept an atmosphere. Water has continued cycling. The planet has endured impacts, ice ages, extinctions, volcanic ages, and continental drift, and still life continued. Not unchanged, but unbroken. The more we search the universe, the more careful we become with words like ordinary. Earth may not be unique. There may be countless worlds with oceans and skies. But at the moment, this is the only living world we know intimately. The only place where consciousness has certainly opened its eyes and asked questions about stars. The only place where the universe, as far as we know, has become aware of itself in the form of living minds. That thought can make Earth feel both small and precious at once. If these quiet journeys through science help you settle into rest, you can subscribe, leave a like, or share where you're listening from tonight. It helps this calm corner of the universe find more people who need it. But for now, there is nothing you need to do except listen, and let the world keep turning beneath you. There is comfort in realizing how much of your life depends on motions and balances you never have to manage yourself. You do not have to keep Earth spinning. You do not have to hold the atmosphere in place. You do not have to tilt the planet towards summer or away from winter. You do not have to paint the sky blue or red. These things simply happen, quietly, with immense consistency. The planet has been carrying out these rhythms long before you arrived, and it will go on doing so while you sleep. That may be one of the softest lessons in astronomy. The universe is not only vast, it is dependable in ways that can feel almost tender. Dawn returns. Seasons lean and turn. Evening colors gather and fade. The air holds light, warmth, and breath. A small rocky world circles an ordinary star, and in that narrow band of possibility, forests grow, oceans move, and living creatures rest beneath a sky made blue by scattered sunlight. Earth is not the center of the cosmos. It is something quieter than that, and in some ways more beautiful. It is a small, moving world that happens to be just gentle enough for us. A place where gravity is firm but not crushing, where air is thin but sufficient, where water flows, where light arrives softened into color, and where a creature like you can lie still at night and think about the universe at all. So as you settle deeper into rest, you might imagine the planet from far away. Not as a map, not as a globe in a classroom, but as a real world, turning slowly in darkness, wrapped in its thin shell of air, clouds drifting across its face, one side in sunlight, the other in night. Somewhere on that turning world is your room, your bed, your breathing, your thoughts gradually becoming quieter. You are resting on a planet that is moving with great speed and great calm. You are held to its surface by gravity, covered by air, warmed by a star, protected by invisible fields and ancient balances. And all around this quiet little world stretches the vastness of space. In the next part of our journey, we will drift a little farther outward, toward the moon, the planets, and the wider architecture of our solar neighborhood. But for now, let yourself stay here, on Earth, in this simple and remarkable place. A small blue world, suspended in darkness, carrying you gently through the night. Part 3, the moon, the planets, and the slow rhythm of the solar system. Now that we have rested for a while on Earth, it feels natural to look just a little farther out. Not yet to the distant stars, and not yet to the deep black beyond the edge of our familiar sky. Just outward enough to meet the quiet neighbors that have been with us all along. The moon above the night horizon. The planets wandering slowly across the dark. The scattered worlds, rings, rocks, and icy edges of the solar system. So much of it has been hanging over human life for thousands of years, seen long before it was understood. And maybe that is part of why the solar system feels so calm. It is mysterious, but not in a harsh way. It is strange, but in a rhythm we can slowly settle into. The moon waxes and fades. Planets brighten, dim, and drift. Seasons return. Tides rise and fall. Even before astronomy became a science, people could feel that something orderly was happening above them. Something patient. Something repeating. So in this part of our journey, we are going to move gently through that quiet neighborhood. We will begin with the moon, because it is the closest thing in the sky that feels almost like a companion. Then we will drift outward through the planets, from the hot inner worlds to the giant outer ones, and finally to the cold belt of distant ice where the solar system begins to thin into darkness. The moon is the easiest place to begin because it feels so familiar. You can see it from almost anywhere on Earth. It has watched over oceans, forests, mountains, cities, deserts, and sleeping streets for all of human history. It feels close, and in cosmic terms, it is. On average, it is about 384,000 kilometers away, which is a long distance for a human being, but a small one for astronomy. And yet the moon does not shine on its own. This is one of the gentlest facts in the sky. The light of the moon is borrowed light. It glows because sunlight falls on its surface and reflects back to Earth. Moonlight is really sunlight, softened by distance and dust and stone. That simple fact explains the phases of the moon. The moon does not grow and shrink in the sky. It is always there as a round world. What changes is how much of its sunlit half we can see from Earth. As the moon orbits our planet, the angle between Earth, moon, and sun changes, and we see different portions of the illuminated side. A thin crescent, a half moon, a swelling gibbous. Then the full moon, bright and complete. After that, the pattern reverses. slowly returning to darkness. There is something deeply soothing about those phases because they are both changing and reliable. The moon never stays the same, yet it never becomes unfamiliar. It moves through a repeating cycle that people in every age have noticed. Farmers, sailors, poets, astronomers, children looking out a bedroom window, all of them have shared that same quiet calendar in the sky. Another reason the moon feels familiar is that we always see nearly the same face. This is because the moon rotates on its axis in the same amount of time it takes to orbit Earth. The result is something called tidal locking. The moon turns, but it turns in step with its orbit, so one hemisphere always faces us. It is not that the far side does not exist. It is simply turned away. That hidden side remained unseen by human eyes until the space age. For most of history, there was a kind of permanent mystery in the moon, a half-known world with a face it never showed us. Even now, there is something beautiful in the fact that our closest neighbor is only partly familiar. It reminds us that even the most constant things can keep part of themselves in shadow. The moon also shapes life on Earth more than we usually notice. Its gravity pulls on our oceans, helping create tides. The water on the side of Earth facing the moon is drawn slightly outward, and the water on the opposite side also bulges for related reasons of orbital motion. As Earth rotates through these bulges, coastlines experience the regular rise and fall of the sea. So even here, as you rest far from any shoreline perhaps, the moon may still be moving water somewhere. Quiet harbors lifting and lowering. Wet sand being uncovered, then covered again. Shorebirds stepping through the exposed edges of the sea. The moon is not only a light in the sky, it is a force touching the oceans. And very slowly, almost impossibly slowly, it is moving away from us. The moon drifts farther from Earth by about 3.8 centimeters each year. That is not enough for anyone to notice in daily life, and not enough to change the beauty of moonlight tonight. But over immense spans of time, it matters. The Earth and Moon are not frozen together in one eternal arrangement. Even this familiar partnership is gently evolving. From the Moon, it is natural to move inward first, toward the Sun, to the small rocky planets of the inner solar system. These worlds are more solid and compact than the giant planets farther out. Each one has its own quiet character, almost as if the solar system were trying several different versions of what a planet could be. Mercury is the closest planet to the Sun. It is small, gray, cratered, and harshly exposed. Because it has almost no substantial atmosphere to hold heat or soften sunlight, its temperatures swing dramatically between day and night. The side facing the Sun can become extremely hot, while the night side can drop into bitter cold. And yet even Mercury, so close to the Sun, contains surprises. In craters near its poles, where sunlight never reaches, there is evidence of water ice. That is one of the softer truths in astronomy. Even in the inner heat of the solar system, shadow can preserve cold. A place can live beside fire and still keep pockets of frost. Venus comes next, and from a distance it might sound almost Earth-like. It is close to our world in size. It is rocky. It is often called Earth's sister planet. But up close, Venus is one of the most unforgiving places in the solar system. Its atmosphere is extremely thick, rich in carbon dioxide, with clouds of sulfuric acid above. The greenhouse effect there is so intense that the surface becomes hotter than Mercury's, even though Venus is farther from the Sun. It is a reminder that distance alone does not decide everything. A world can stand at a safer distance from the Sun and still become an oven if its atmosphere traps enough heat. Venus teaches that a planet's sky can change its destiny. And Venus has another strange quality. It spins very slowly, and in the opposite direction from most planets. This means the Sun would appear to rise in the west and set in the east. A single day on Venus, measured by one full rotation, is longer than its year. It turns so slowly that its own sunrise takes on a very different meaning from ours. On Earth, dawn feels daily. On Venus, day and year lose the relationship we are used to. Then we return home for a moment in our minds, to Earth, the third planet, the blue one, the one with oceans, weather, and breathing things. After Venus and Mercury, Earth almost feels miraculous in its moderation. Not because it is perfect, but because it is balanced enough. A world of clouds, liquid water, moving air, stable cycles, and the long persistence of life. Beyond Earth comes Mars, perhaps the most quietly haunting of the planets. Red from iron-rich dust, cold, dry, and thin-aired, it looks like a place that once held more than it does now. Its day is remarkably close to Earth's, only about 40 minutes longer. Its seasons also come from axial tilt, much like ours, though they last longer because Mars takes more time to circle the Sun. There is a reason Mars captures the imagination so easily. It feels both alien and almost familiar. It has polar ice caps. It has weather. It has ancient river valleys and signs that liquid water once moved across its surface long ago. It is not a living Earth, but it carries hints of a world that may once have been wetter, warmer, and more active than the desert planet we see now. And then there are the sunsets on Mars. On Earth, sunsets glow red and orange because blue light scatters more easily out of the direct path. On Mars, with its very different dusty atmosphere, sunsets near the Sun can appear blue. That reversal feels almost dreamlike. Another sky, another world, another evening where the familiar colors are rearranged. Between Mars and Jupiter lies the main asteroid belt, often imagined as a crowded field of tumbling rocks. In truth, it is far emptier than many films suggest. The asteroids are spread across a huge region, often separated by vast distances. But taken together, they tell an old story. They are leftovers from the early solar system, material that never combined into a full planet, likely because Jupiter's gravity disturbed that process. These rocky bodies are like preserved fragments from the solar system's youth, ancient pieces that remained scattered instead of gathering. Broken beginnings, perhaps, or building blocks that never finished building. There is a kind of quiet dignity in that, too. Not everything in the universe is meant to become complete. Some things remain as traces of what almost was. Then we reach Jupiter, and the scale changes dramatically. Jupiter is enormous. It holds more mass than all the other planets combined, yet it is not a solid world in the way Earth or Mars are. It is mostly hydrogen and helium, a giant sphere of gas and deeper fluid layers, with a small core hidden far below. If the inner planets feel like places you might stand, Jupiter feels more like a weather system given planetary size. Its atmosphere is striped with bands of cloud and driven by immense winds. Storms larger than Earth move through its upper layers. The most famous of these, the Great Red Spot, has lasted for centuries, though it changes in size and shape over time. To imagine a storm persisting that long is to begin feeling how different time can be on another world. And Jupiter has many moons, each one a small world of its own. Some are cratered. Some are volcanic. Some may hide oceans beneath ice. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. Europa, another of Jupiter's great moons, likely holds a vast ocean under its frozen outer shell. Beneath that ice, in darkness, there may be more liquid water than in all Earth's surface oceans combined. That possibility has a special kind of silence to it. A hidden sea under a moon of ice, far from the warmth of our familiar world. No sunlight touching the water. No open waves. Just an ocean sealed below frost and stone, moving in darkness around a giant planet. The solar system is full of these unexpected forms of beauty. Not always warm, not always welcoming, but beautiful all the same. Beyond Jupiter lies Saturn, perhaps the most visually graceful of all the planets. Its rings make it seem almost unreal, as though it were designed more by imagination than by gravity. But the rings are real, and they are not solid. They are made of countless particles of ice and rock, ranging from tiny grains to pieces as large as buildings, all orbiting Saturn together in flattened bands. Seen from far away, the rings appear smooth, almost delicate. But they are really a vast swarm of separate fragments, each following its own path. Saturn teaches a quiet lesson there. What looks continuous from a distance can be made of countless separate things moving in harmony. The rings are also surprisingly thin compared with their enormous width. In some places, they are only tens of meters thick. That feels almost impossible when you first hear it. A structure so broad and luminous, yet so shallow. The solar system often works this way. Grandeur held in delicate forms. Saturn's moons, too, are remarkable. Titan, its largest moon, has a thick atmosphere and lakes of liquid methane and ethane on its surface. It is one of the most Earth-like places in the solar system in some ways, and one of the most alien in others. Rivers and rain exist there, but not of water. It is like a cold echo of the patterns we know, repeated in unfamiliar chemistry. After Saturn, sunlight grows weaker, and the worlds become colder and more distant. Uranus is the first of the ice giants. It is pale blue-green because of methane in its atmosphere, which absorbs red light and reflects the cooler colors we see. But its strangest feature is its tilt. Uranus is tipped over so dramatically that it essentially rotates on its side. This gives Uranus a very different relationship with the Sun. For long stretches of its year, one pole points almost directly toward the Sun while the other points away. The result is seasons unlike anything on Earth, lasting for decades. Imagine a place where the Sun remains above the horizon for years, then disappears for years. A world where the concept of sunrise and sunset stretches far beyond anything in ordinary human life. Neptune, the farthest major planet, is another ice giant, deeper blue and swept by fierce winds. Even at that great distance from the Sun, its atmosphere is active, with storms and fast-moving weather. It takes about 165 Earth years to orbit the Sun. Since its discovery in the 19th century, it has completed only a small number of full journeys around our star. That alone can calm the mind a little. On Neptune, a year is so long that entire human lifetimes fit inside a single orbit. The pace of things there makes our own yearly rhythms feel very brief. The solar system contains not one clock, but many. And then, beyond Neptune, we begin to leave the classical planetary neighborhood and enter a colder, looser region known as the Kuiper Belt. This is a vast zone of icy bodies and dwarf planets, including Pluto. For many people, Pluto still holds a gentle affection, whether called a planet or not. Small, distant, and dim, it circles the Sun in a long tilted orbit, taking about 248 Earth years to complete one journey. Pluto is not alone out there. It belongs to a wider family of icy objects, remnants of early formation, preserved in the cold outer reaches. In a way, the Kuiper Belt is like the solar system's memory. Material left over from the beginning, stored at the edges where temperatures stay low and change happens slowly. Far beyond even that lies the Oort cloud, a distant spherical shell of icy bodies thought to surround the solar system at unimaginable distances. We have not seen it directly as a whole, but many long-period comets are thought to come from there. If the inner planets feel like home, and the gas giants feel like the wide countryside, then the Oort cloud is more like the dark outer boundary where the solar system blurs into interstellar night. And still, despite all this variety, the solar system is one connected place. The planets formed from the same rotating disk of gas and dust around the young Sun. The asteroids, moons, comets, and rings all belong to that same long history. It is not a random collection. It is a family of outcomes shaped by distance, gravity, chemistry, collision, and time. There is something especially calming about that. The planets are different not because the universe changed its mind each time, but because small differences in place and condition led to different stories. Closer to the Sun, hotter worlds emerged. Farther out, gas giants gathered. Beyond them, cold belts of ice remained. The same beginning, many expressions. If these quiet explorations are helping you wind down, you can subscribe, like, or leave a comment about where you're listening from tonight. It helps more night travelers find this calm little signal in the dark. But there is no need to move. No need to do anything now. Just keep drifting. As we move through these worlds in the imagination, it becomes easier to feel what the solar system really is. Not just a chart in a textbook. Not just names learned in childhood. It is a layered, living architecture of motion. Worlds circling a star. Moons circling worlds. Rings spread thin and shining. Rocks drifting. Ice waiting in darkness. All of it held together by gravity, and all of it moving with patient regularity. Our own life unfolds inside this greater rhythm. When you look at the moon, you are seeing part of Earth's immediate relationship with space. When you notice the bright point of Jupiter or Venus in the evening sky, you are seeing another world sharing the same sun. When a comet appears unexpectedly, with its pale tail stretched across the dark, you are witnessing ancient ice visiting the inner solar system for a brief luminous moment. That may be one of the most peaceful ideas in astronomy. The night sky is not separate from us. It is not merely decoration above human life. It is the visible surface of the larger system we live inside. Earth is not beneath the sky. Earth is in it. And even now, while you listen, the moon may be lifting ocean tides somewhere. Jupiter's storms may still be turning. Saturn's rings may be scattering sunlight into the cold. Mars may be holding its blue sunset over a dusty horizon. Neptune may be carrying its long weather through the edge of the sun's reach. Pluto may be continuing its distant orbit in almost total quiet. None of it asks for our attention. None of it stops when we sleep. The solar system keeps its own patient rhythm whether we are watching or not. So let that be the feeling you rest with at the end of this part. Not just that there are other worlds, but that they move in a slow, ordered dance around the same star that warms Earth by day. A shared center. A shared origin. A wide neighborhood of very different places, all bound together in silence and motion. In the next part, we will go beyond the planets and look more closely at the sun and the stars themselves, those glowing furnaces that light the dark and quietly shape everything around them. But for now, let your thoughts remain here, in the solar system, among the moon, the rings, the red dust, the blue giants, and the distant belts of ice. A quiet family of worlds, circling steadily in the dark, while Earth carries you gently towards sleep. Part 4, The Sun and the Quiet Life of Stars. Now that we have drifted past the planets and the slow architecture of the solar system, it feels natural to lift our eyes a little farther. Beyond the moon, beyond Mars, beyond Saturn's rings and the cold outer worlds, there is the source of almost all the light we know by day, the sun. And beyond the sun, scattered through the dark in numbers too large to hold in the mind, there are the stars. At first, stars can seem simple. Just small points of light, tiny silver marks in the sky. But that simplicity is only what distance does to them. In truth, each star is its own place of fire and gravity, its own long life, its own story unfolding over immense spans of time. Some are young. Some are ancient. Some burn softly for trillions of years. Some live quickly and vanish in violent endings. And somewhere among them is our own quiet star, the one that makes mornings possible on Earth. In this part of our journey, we are going to stay with the stars. We will begin with the sun, because it is the nearest and most intimate one. Then we will move gently outward into the wider population of stars, looking at how they are born, why they shine, what their colors mean, how long they live, and what remains when their long burning finally comes to an end. It is easy to forget that the sun is a star because it feels so different from the stars of night. It is not a pinprick. It is warmth on skin, light through curtains, pale gold across the floor in morning. But the sun is not separate from the stars. It belongs to them. It is simply much, much closer than the others. The Sun sits about 150 million kilometers from Earth. That is an immense distance in human terms, and yet it is small by the standards of the cosmos. Light from the Sun reaches us in about 8 minutes and 20 seconds. So even sunlight is a kind of message from the recent past. When morning light touches the edge of a building, or falls quietly across your room, it has already been traveling through space for several minutes before it arrives. That light feels immediate to us, but it is not truly immediate. Astronomy begins, again and again, with this soft lesson. To see is to receive something that has traveled. The Sun itself is a middle-aged star, about 4.6 billion years old. It formed from a cloud of gas and dust long before Earth existed, and it has been shining steadily for most of the solar system's history. There is something reassuring in that steadiness. Human history is short. Civilizations rise and fall. Languages change. Coastlines shift. And through all of it, the Sun has continued its quiet work, rising over oceans, forests, deserts, and cities, one day after another. But the Sun is not burning like wood or coal burns. It does not shine because of fire in the ordinary earthly sense. The power of a star comes from nuclear fusion in its core. Deep inside the Sun, gravity presses hydrogen atoms so tightly together that they fuse into helium. In that process, a tiny amount of mass is converted into energy. That energy begins a long journey outward, eventually leaving the Sun as light and heat. This means the sunlight you know began in unimaginable pressure, deep within the heart of a star. It is strange and beautiful to think that the warmth on your skin, the gold on leaves, the brightness of afternoon clouds, all began in the compressed interior of a glowing sphere held together by its own gravity. The Sun contains almost all the mass in our solar system. Everything else, all the planets and moons and asteroids and comets, together make up only a small remainder. In that sense, the solar system is not really a collection of equal partners. It is mostly the Sun, with other worlds moving within its influence. And yet the Sun does not feel heavy in our lives. It feels gentle. We know it through dawn, through daylight, through warmth, through the slow passing of shadows. We know it through life itself, because nearly every food chain on Earth begins with sunlight. Plants take in light and turn it into stored energy. That energy moves through ecosystems, through forests and fields and oceans. Even the breath you take is part of a system powered, directly or indirectly, by a nearby star. So when we say that the Sun is the center of the solar system, that is not only a matter of orbit. It is also a matter of dependence. Life on Earth exists in relationship with the Sun in more ways than we can easily count. And still, the Sun is not unusual in the grand cosmic sense. It is not the largest star, not the hottest, not the brightest. It is a fairly ordinary yellow-white star, one among vast numbers in the Milky Way. This is another quiet comfort. Earth was not given life by some singular cosmic miracle blazing in a category of one. It formed around a star that is, in many ways, ordinary. The universe may produce such possibilities more often than we once imagined. If you look up at the night sky, the stars appear white to many eyes, though some can seem faintly blue, reddish, or golden. These colors are not decoration. They tell us something about temperature. In general, blue stars are hotter than white ones, white stars hotter than yellow, yellow hotter than orange, and orange hotter than red. A red star may look warm in color, but in stellar terms it is cooler than a blue one. That reversal can feel unintuitive, but it is part of the quiet language of stars. A star's color is a clue to how hot its surface is. Our Sun, with its yellow-white light, sits somewhere in the middle compared to many others. Some stars burn at temperatures far higher and appear blue or blue-white. Others are cooler and glow orange or red. This means that when you look at a starry sky, you are not just seeing many lights. You are seeing variation, different temperatures, different sizes, different life stages, different stories, each compressed by distance into a point. And stars differ not only in color, but in size and brightness. Some are smaller than the Sun, some are much larger. The largest stars known can be so enormous that if placed where our Sun is, they would extend far out into the solar system, swallowing the inner planets. Yet size alone does not tell the whole story. A star's mass is especially important, because mass shapes its life. That is one of the central truths of stellar astronomy. The fate of a star is largely written by how much matter it begins with. But before a star can live, it must be born. Stars are born in great clouds of gas and dust called nebulae. These vast regions of space can seem soft and almost dreamlike in telescope images, glowing in pinks, blues, and deep shadow. But beneath that beauty, they are places of slow construction. Gravity pulls material together. Clumps form. Denser knots gather more matter. Over immense spans of time, some regions become compact enough, hot enough, and pressured enough for fusion to begin. That moment is the true birth of a star. So when we see a star, we are seeing a successful collapse. A cloud that did not remain diffuse. A patch of the universe where gravity slowly gathered enough material to light a furnace. Stars are born not in haste, but in patience. Sometimes it takes millions of years before a new star fully settles into its long, stable life. There is something peaceful about that. Even the lights of the cosmos begin in darkness and slow accumulation. Many stars are not born alone. They often form in clusters, emerging from the same cloud at roughly the same time. That means the sky is filled not only with solitary stars, but with families of stars that began together. Some remain loosely associated, moving through space as part of open clusters. Others belong to much older and denser globular clusters, ancient spherical swarms of stars that orbit the outskirts of galaxies like glittering fossils from the early universe. If you could stand far enough away and look at such a cluster, it would not seem like a few scattered points. It would seem like a concentrated city of light. Some stars also live in pairs. In fact, many stars belong to binary systems, where two stars orbit a common center of gravity. Others belong to even more complex systems. So the Sun, traveling alone, may be a little less common than the imagination first expects. Across the galaxy, many stars move not in solitude, but in partnership. These stellar pairings are useful to astronomers because they reveal how mass works in motion. But even without the math, there is something beautiful in the idea that some stars spend their whole lives in orbit around one another, bound across unimaginable distances by gravity alone. Our own Sun will not last forever, though its lifetime is vast compared with ours. Right now it is in the main and longest phase of its life, steadily fusing hydrogen in its core. This stage will continue for billions of years more. But eventually, the supply of easily fused hydrogen in the center will run low. When that happens, the balance inside the Sun will begin to change. Gravity is always trying to compress a star inward. Fusion pushes outward. A star lives by balancing those two forces. As long as fusion continues strongly enough in the core, the star remains stable. But when the core changes, the star must change too. In the case of the Sun, the future is not sudden. It is slow, vast, and far away. Billions of years from now, the Sun will swell into a red giant. Its outer layers will expand dramatically. Mercury and Venus will almost certainly be lost. Earth's fate in that era is more complicated, but in any case our world will not remain the place it is now. The Sun that currently gives life will eventually become too swollen and too bright for the familiar Earth to survive as it is. Yet even this transformation is not violent in the way we often imagine cosmic endings. For a star like the Sun, the ending is more like a gradual release. After its giant phase, it will shed its outer layers into space, forming a glowing shell of gas called a planetary nebula. The name is misleading, because it has nothing to do with planets. Early observers simply thought such objects looked planet-like through small telescopes. In truth, They are the soft remains of dying stars, illuminated by the hot central core left behind. What remains at the center will be a white dwarf. A white dwarf is not a giant white star. It is a small, dense stellar remnant, roughly Earth-sized but containing a large fraction of the Sun's mass. No longer powered by active fusion, it shines because it is still hot. Over unimaginable spans of time, it cools and fades. So the future of the Sun is not a sudden disappearance. It is a long dimming. There is something surprisingly gentle in that image. Our star will not explode in a final blaze that tears the solar system apart. It will expand, release its outer layers, and settle into a dense ember, cooling slowly in the dark. But not all stars end so quietly. More massive stars live very different lives. They are brighter, hotter, and often bluer. But that brilliance comes at a cost. A massive star burns through its fuel far more quickly than a smaller one. So in one of the universe's most striking inversions, the largest stars often live the shortest lives. They burn harder and die younger. A small red dwarf, dim and cool by stellar standards, can live for trillions of years. That is longer than the current age of the universe. In fact, the cosmos is still too young for any red dwarf to have finished its full life naturally. They are the long-burning candles of the universe, patient and economical with their fuel. Massive blue stars are the opposite. They can shine with astonishing intensity, but they do not last nearly as long. Some exhaust their fuel in only millions of years, a brief life compared with the Sun's calm multi-billion-year timescale. They arrive bright, live fast, and meet more dramatic ends. When a truly massive star runs out of fuel in its core, the balance between inward gravity and outward pressure collapses. The core can no longer support the layers above it. The star falls inward, then rebounds in one of the most powerful explosions in the universe, a supernova. For a brief time, a supernova can outshine an entire galaxy of ordinary stars. A single star reaches a brightness so immense that it becomes visible across vast intergalactic distances. Yet even that dazzling event is not just destruction. It is also distribution. Supernovae scatter heavy elements into space, enriching future clouds of gas and dust. This matters more than it first appears, because the universe did not begin with all the elements needed for worlds like Earth or bodies like ours. The early universe was mostly hydrogen and helium, with trace amounts of a few lighter elements. The heavier elements, carbon, oxygen, silicon, iron, and many more, were forged inside stars and spread outward through stellar death. So in a very literal way, stars are the source of the deeper material complexity of the universe. The carbon in living things, the oxygen we breathe, the calcium in bones, the iron in blood, all of these have a history that runs back through stars. This is one of the most repeated ideas in astronomy, but it remains moving no matter how often it is heard. You are not merely standing under the stars. You are built from the kind of matter stars made possible. The story of your body begins before Earth, before the Sun, in older generations of stellar life and death. And after some supernovae, the central remnant left behind becomes a neutron star. These objects are among the densest things in existence. A neutron star packs more mass than the Sun into a sphere only about the size of a city. Matter there is compressed beyond anything familiar. The result is so extreme that ordinary language begins to fail. A spoonful of neutron star material, if it could somehow be brought to Earth unchanged, would weigh an unimaginable amount. Some neutron stars spin rapidly and emit beams of radiation from their magnetic poles. As those beams sweep across space, they can be detected as steady pulses, like the beam of a lighthouse crossing darkness. These are pulsars. Their regularity is so precise that when they were first discovered, astronomers jokingly wondered whether they could be signals from intelligence. But they were something more elegant than that, the rhythmic remnants of collapsed stars. And for the most massive stars of all, even the neutron star stage may not be enough. Gravity may continue the collapse further still, leading eventually to black holes. We will linger with those strange objects in a later part of our journey. For now, it is enough to feel how wide the range of stellar endings can be. Some stars dim quietly into white dwarfs. Some explode and leave neutron stars. Some collapse so deeply that light itself cannot escape. All of this, the entire life cycle of stars, begins from clouds and gravity, from dark material gathering, from long invisible preparation, then ignition, then long eras of light, then transformation. If these calm explorations help you unwind, you can subscribe, leave a like, or share what part of the world you're listening from tonight. It helps others find this quiet place. But there is nothing you need to do right now. Just keep resting, and let the stars continue their ancient work above you. When we look at stars from Earth, one of the first things we notice is their twinkling. They shimmer, flicker, and seem almost alive in the night sky. But the stars themselves are not really twinkling in the way they appear to us. That trembling quality comes mostly from our own atmosphere. As starlight passes through layers of moving air with slightly different temperatures and densities, it is bent and distorted. The result is that the star's apparent brightness and position shift from moment to moment. So the twinkle of starlight is not the star trembling. It is Earth's air, gently unsettling the light on its way to us. There is something lovely in that, too. Even our experience of the stars is shaped by the world we stand on. We do not see them from nowhere. We see them through air, from a spinning planet, under a magnetic sky, with human eyes and human time. And still, even filtered through our atmosphere, the stars reach us. Some of the light entering your eyes on a clear night began its journey years ago. Some began decades ago. Some, from distant stars or faint unresolved starlight in the Milky Way, has been traveling far longer. Night itself becomes a kind of archive. The sky is not just full of objects. It is full of arrival times. That changes the feeling of stargazing. To look upward is not simply to look far. It is also to look back. So as this part draws toward its close, perhaps let the idea settle gently in your mind that stars are not decorations scattered across darkness. They are long-lived engines of light and matter. They are born from cold clouds. They spend ages balancing gravity and fusion. They color the sky with clues about temperature and age. They live alone or in pairs, in clusters or across galactic arms. They make the conditions for planets, for chemistry, and perhaps for life. And when they die, they do not merely vanish. They leave remnants, release elements, and reshape the future. The Sun, which feels so personal to Earth, is one chapter in that larger stellar story. A calm star among many, giving our world its days, its weather, its energy, and its long chance at life. The stars beyond it are more distant, but not entirely separate. They belong to the same wider order. They are kin to our Sun, though each lives its own version of the stellar life. In the next part of our journey, we will step farther out again, beyond individual stars, and into the wider architecture of the Milky Way and the quiet realm of galaxies. But for now, rest here for a moment among the stars themselves. Imagine them not as points, but as real luminous bodies suspended across immense space. Some just being born in dark nebulae. Some shining steadily in long middle age. Some swelling toward their endings. Some already gone, their light still traveling. And somewhere among them, our own Sun, rising and setting over Earth with such regular faithfulness that it can almost feel eternal, even though it, too, belongs to this larger cycle of beginning, shining, changing, and dimming. A sky full of fires. A universe full of long lives. And beneath one ordinary star, on one small living world, you are resting safely in the dark. Part 5, The Milky Way and the Quiet Realm of Galaxies. Now that we have rested for a while among the stars, it feels natural to move one step farther out. Not away from the stars, exactly, but around them. Beyond the life of any single sun, beyond the warmth of any one solar system, There are larger structures, vast gatherings of stars held together by gravity over unimaginable distances. These are galaxies, great islands of light drifting through the dark. From Earth, the night sky can make the universe seem scattered. A star here, another there, a pale haze overhead on very clear nights. But much of that appearance comes from where we are standing. We are not outside the Milky Way looking in. We are inside it, deep within one of its spiral arms, surrounded by its stars, dust, and gas. Our view is the view from within the structure, like trying to understand the shape of a forest while standing among the trees. In this part of our journey, we are going to stay with that larger scale. We will begin with our own galaxy, the Milky Way, because it is our true cosmic home beyond the solar system. Then we will drift outward to other galaxies, to star clusters, to galactic motion, to the quiet possibility of collisions, and to the small place our own galaxy occupies among its neighbors. The farther we go, the more the universe begins to resemble not a scattered emptiness, but a patterned and patient architecture of light. The word galaxy can sound abstract until you pause over what it means. A galaxy is not just a group of stars. It is an immense gravitational system made of stars, gas, dust, dark matter, and often a supermassive black hole at its center. It is a long-lived structure, held together not by coincidence, but by gravity acting over billions of years. That means our sun is not just floating randomly through space. It belongs to a galaxy. Earth belongs to a galaxy. Everything familiar to us, every ocean, city, mountain, and sleeping room, is moving within a far larger system than daily life suggests. We do not simply live in a solar system. We live in the Milky Way. The Milky Way is a barred spiral galaxy, a broad rotating system with spiral arms curving outward through space. If we could somehow travel far above it and look down, we would not see a random cloud of stars. We would see a luminous disk with curved arms winding away from a bright central region. It would look less like a scattered spray and more like a great, rotating pattern. But from Earth, we cannot step outside and look down. What we see instead is the Milky Way stretched across the sky as a pale, misty band. On a dark night, far from city lights, it can appear as a river of dim glow arching overhead. For most of human history, that band was one of the most mysterious things in the sky. It looked like spilled milk, or smoke, or light too diffuse to explain. The reason it appears that way is beautifully simple. We are inside the disk of the galaxy, and when we look along the crowded plane of that disk, we see the combined light of countless distant stars blended together. The Milky Way in the sky is not one object floating apart from the rest. It is the inner glow of our own galactic home seen from within. That alone is enough to change the feeling of the night sky. When you look up and see that pale band, if the sky is dark enough to reveal it, you are not looking out at some separate thing. You are looking through the crowded interior of the structure you live inside. It is as if the walls of your house were made of distant starlight. The Milky Way is vast. It is often described as being around 100,000 light-years across, though different ways of measuring its outer structure can push estimates higher. Even the smaller figure is so large that ordinary imagination cannot comfortably hold it. Light, moving faster than anything else in the universe, would still need about 100,000 years to cross the galaxy from one side to the other. And yet our solar system occupies only a tiny corner of it. The Sun does not sit near the center of the Milky Way. It lies out in the disk, within a smaller spiral structure often called the Orion Arm or Orion Spur, about halfway or a little more than halfway from the galactic center. This is another quiet act of demotion from astronomy. Earth is not the center of the solar system. The Sun is not the center of the galaxy. And the Milky Way itself is not the center of the universe. Again and again, science has invited us away from centrality and toward perspective. But there is comfort in that too. The universe is not arranged like a spotlight aimed at us. It is wider, calmer, and less personal than that. And still, within that vastness, our corner matters to us because it is where life happened. A small orbit around an ordinary star, in a minor arm of one galaxy among many, became the setting for consciousness. Astronomers estimate that the Milky Way contains hundreds of billions of stars, perhaps more. The exact number is hard to know because dust obscures many stars from direct view and because counting on that scale is never perfectly neat. But even a lower estimate leaves the mind stunned. Hundreds of billions of stars in one galaxy, and around many of those stars, likely planets. That means the Sun is not rare in the sense of being one among a few. It is one among staggering numbers. So if you ever feel the night sky becoming larger in your imagination, that feeling is not misleading. It is accurate. The Milky Way alone contains more stars than any ordinary thought can comfortably count. And still, for all that immensity, the galaxy has its own internal order. The stars are not standing still. The Milky Way rotates. Its stars orbit the galactic center, each following paths shaped by gravity. Our Sun is part of that motion. It is moving through the galaxy all the time, carrying Earth and the rest of the solar system along with it. One full orbit around the center of the Milky Way takes the Sun roughly 230 million years. This is sometimes called a cosmic year or galactic year. The last time our solar system was in roughly this same region of its galactic orbit, the world on Earth was unimaginably different. Dinosaurs had not only appeared, they would eventually rise and vanish within that broader span. Human history is so brief compared with a galactic orbit that it barely registers. That comparison can be strangely calming. The problems of a week, or even a lifetime, take on a different texture when placed beside the slow turning of a galaxy. This does not make human life meaningless. It makes it tender. Brief things can still matter deeply. Perhaps even more so because they are brief. The galaxy also contains different neighborhoods, if we may use that word gently. There are spiral arms richer in gas and dust, where new stars can form more readily. There are older populations of stars spread more broadly through the galactic disk and the surrounding halo. There are dense star clusters, glowing nebulae, dark dust lanes, and regions so crowded that the sky would look very different from the one above Earth. Nebulae are among the most beautiful parts of galactic structure. These are clouds of gas and dust within galaxies, and they can play different roles. Some are stellar nurseries, where gravity gathers material into new stars. Others are the softly glowing remains of dying stars, expanding into the surrounding medium. Some appear bright because they are energized by nearby stars. Others appear dark, not because they are empty, but because they are so dense with dust that they block the light behind them. A dark nebula is a lovely paradox. Something so full that it looks like an absence. In images of the Milky Way, some of the black rifts through the brighter band are not holes in the galaxy. They are dense dust clouds obscuring what lies beyond. So even darkness in the galaxy can be a sign of material, of richness, of something present but unlit. Star clusters also bring their own quiet variety. Open clusters are generally younger and looser gatherings of stars, often formed from the same cloud and still drifting together through space. Globular clusters are older, denser, and far more ancient, spherical swarms of stars orbiting the galaxy in its halo. Many globular clusters are relics from very early in galactic history. They contain stars that formed long ago, making them among the oldest visible structures associated with the Milky Way. If open clusters can feel like youthful communities, then globular clusters feel like old libraries. Dense, ancient, and full of stellar histories, still moving in quiet orbits around the larger galaxy that holds them. At the center of the Milky Way lies something stranger still. A supermassive black hole known as Sagittarius A star. Its mass is about 4 million times that of our Sun. We do not see the black hole directly, because black holes do not emit light in the ordinary sense. but astronomers can track the orbits of stars near the center and infer the enormous mass concentrated there. It is one of the most astonishing things about galaxies that at their hearts there often seems to be something dark, dense, and extreme. A hidden gravitational anchor around which the wider luminous structure is organized. We will spend more time with black holes later, but even here, within the realm of galaxies, they wait quietly in the middle, like secret centers. And still the Milky Way is only one galaxy. Beyond it lie many others, each with its own form and history. Some are spiral galaxies like our own, with graceful arms curving through the dark. Others are elliptical galaxies, rounder or more stretched in shape, often containing older stars and less active star formation. Others are irregular, lacking a clear ordered structure, shaped perhaps by interactions, collisions, or more chaotic histories. This variety matters because galaxies are not all built the same way. They grow, merge, evolve, and interact. Their shapes carry clues about what they have experienced. Spiral galaxies tend to be rich in gas and dust, often forming new stars in their arms. Elliptical galaxies can be smoother and quieter, with less cold gas available for new star birth. Irregular galaxies can look ragged, as though their structure has been disturbed or never fully settled. The universe does not create one single galactic template and repeat it endlessly. It allows for a wider range of outcomes. Some galaxies are small dwarf galaxies, containing far fewer stars than giants like the Milky Way. Others are colossal systems stretching across immense distances. And though we often imagine galaxies as isolated islands, they are not truly isolated. Gravity draws them into groups and clusters. Our galaxy belongs to a modest gathering called the local group. This is a collection of more than 50 known galaxies, though many are small dwarf members. The two largest are the Milky Way and the Andromeda Galaxy. A third substantial member is the Triangulum Galaxy. Around these larger systems orbit many smaller dwarf galaxies, like attendants moving around brighter centers. Andromeda is especially important because it is our nearest large galactic neighbor, about 2.5 million light-years away. On a dark night, under excellent conditions, it can actually be seen with the unaided eye as a faint smudge of light. That soft blur is an entire galaxy, containing perhaps 1 trillion stars, though estimates vary. To think that human eyes can detect another galaxy across such distance, even as a dim haze, is one of the quieter wonders of stargazing. But Andromeda is not simply sitting still across the void. It is moving toward us. Over billions of years, the Milky Way and Andromeda are expected to approach, interact, and eventually merge. This can sound violent at first, like two great masses crashing into one another. But on the scale of individual stars, collisions are unlikely because the distances between stars are so large. Instead, the merger will be more like an immense gravitational dance. The shapes of both galaxies will distort. Their stars will be redistributed. Tidal tails of material may stretch out. Over long spans of time, the two systems may settle into a new, larger galaxy. That image can be surprisingly peaceful when imagined slowly enough. Not a sudden impact, but a vast reshaping over eons. Two spiral systems, approaching, curving around one another, their forms gradually unwinding and combining. Even galactic collision, when seen on its true timescale, becomes less like an explosion and more like choreography. Galaxies also gather into larger structures called clusters. Some clusters contain hundreds or even thousands of galaxies, all bound together by gravity. Between the galaxies lies not only darkness, but also hot gas and the invisible influence of dark matter. These clusters are among the largest gravitationally bound structures in the universe. And if we zoom out even farther, galaxies and clusters are arranged in patterns that form the cosmic web, a large-scale structure of filaments and nodes surrounding vast emptier regions called voids. That lies just beyond the immediate focus of this part of our journey, but even here it is useful to feel the direction in which the scale opens. Galaxies are not the end of structure. They are part of larger and quieter architectures still. For now, though, it is enough to rest with galaxies themselves, with the idea that stars gather into systems, that those systems rotate, evolve, and sometimes merge, that our own sun is one small light inside one such system, that the pale band of the Milky Way is the inside view of our home galaxy, that the Andromeda glow is another great city of stars crossing unimaginable darkness toward us over time too large for ordinary concern. If these calm explorations are helping you drift towards sleep, you can subscribe, leave a like, or share where in the world you are listening from tonight. It helps more people find this quiet corner of the cosmos. But there is nothing for you to do right now except keep listening, and let the scale of things grow softer around you. There is a special humility that comes with galaxies. A star can already make us feel small, but a galaxy places even stars into a larger belonging. Our sun, powerful enough to light Earth and hold all the planets in orbit, becomes just one point among hundreds of billions. And the Milky Way, immense beyond easy imagination, becomes just one galaxy among countless others. Yet there is no cruelty in that perspective. Smallness is not the same as insignificance. A single room may be small compared with a city, and still be the place where a child sleeps safely. A single note may be brief, and still be the note that makes a whole piece of music ache with beauty. Earth may be small. The solar system may be a tiny corner of the galaxy. The galaxy may be one among many. And still, here in one minor spiral arm, something rare happened. Matter looked up. Life became aware. The universe, in one small place, grew quiet enough to wonder about itself. That makes the Milky Way feel different. Not merely like a structure of stars, but like the larger home in which our local story became possible. And perhaps that is the softest feeling to carry out of this part of the journey. Not just that the Milky Way is large, or that galaxies drift through darkness, but that home can exist on many scales. A room can be home. A planet can be home. A solar system can be home. And beyond that, there is the wider, dimly glowing home galaxy, carrying us along in one spiral arm as it slowly turns. So as you rest, imagine the Milky Way not from the viewpoint of a diagram, but as a real structure around you. A broad disk of stars and dust, arms curving through blackness, nebulae glowing faintly in distant regions, ancient clusters hanging in the halo, a crowded central bulge with something dark and massive at its heart. Our sun moving quietly around that center, taking hundreds of millions of years to complete one orbit. Earth moving with it, you moving with Earth, all of it joined into one layered motion. And somewhere beyond, Andromeda shining faintly in the dark, already on its long approach. In the next part of our journey, we will move into stranger territory, toward black holes and the more extreme side of space, where gravity bends light and the familiar rules of time begin to soften. But for now, remain here a little longer in the calm realm of galaxies. A night sky that is not empty, but inhabited by structures larger than thought. A universe made not only of stars, but of great revolving islands of them. And within one such island, in one quiet arm of the Milky Way, you are resting safely, while the galaxy turns very slowly around you in the dark. Part 6, Black Holes and the Quiet Extremes of Space. Now that we have drifted through the Milky Way and the slow realm of galaxies, it feels natural to move into a stranger part of the universe. Not louder. Not harsher, at least not in the way the imagination often makes it. Just stranger. More extreme. A region of thought where gravity grows deep, time becomes less familiar, and some of the universe's most powerful objects reveal themselves not through brightness, but through absence. This part of our journey is about black holes, and about the broader idea of extreme space. These are the places and objects that seem, at first, almost too strange to belong to the same universe as us. Collapsed stars, invisible wells of gravity, dense remnants smaller than cities, regions where light bends, clocks slow, and matter behaves in ways that feel more like thought experiments than reality. And yet they are real. That may be the most calming way to begin. Black holes are not fantasy. They are not symbolic darkness or cosmic monsters hiding in the sky. They are part of nature. Unusual, yes. Extreme, yes. But still natural. They belong to the same universe as oceans, trees, moonlight, and the quiet turning of Earth. When many people first hear the words black hole, they imagine something like a giant vacuum cleaner in space, roaming through the universe and swallowing everything around it. It is an understandable image, but it is not quite right. A black hole does not pull things in from across the cosmos the way a hungry machine might. If our sun were somehow replaced by a black hole of exactly the same mass, Earth would not suddenly be dragged inward. It would continue orbiting at roughly the same distance, because gravity at that range depends on mass, not on whether the mass belongs to a star or a black hole. That is one of the first soft corrections astronomy offers us. Black holes are not magical devourers. They are extreme gravitational objects, and like other massive bodies, they influence things around them according to distance and motion. So what is a black hole? At its simplest, a black hole is a region of spacetime where gravity has become so strong that nothing, not even light, can escape once it passes a certain boundary. That boundary is called the event horizon. It is not a surface you could stand on, like the ground of a planet. It is more like a threshold, a point of no return. Outside it, escape is still possible. Inside it, all possible paths lead inward. There is something deeply quiet about that. A black hole does not have to roar. It does not need to flash. It can simply exist, dark and invisible, shaping the space around it. Most black holes begin with stars. As we explored earlier, stars live by balancing inward gravity against outward pressure from fusion in their cores. For much of a star's life, those two forces hold each other in check. But if a very massive star exhausts its fuel, that balance can collapse. The core may fall inward under its own gravity so completely that no known force can stop it. If enough mass is packed into a small enough region, a black hole can form. That is one of the most remarkable transformations in nature. A star, once a source of light, becomes a place from which light cannot leave. And yet even here, the story is not always violent in the same obvious way. Some stars explode in brilliant supernovae before leaving behind black holes or neutron stars. Others may collapse more quietly, almost vanishing from view. Nature does not always announce its most profound changes with spectacle. Sometimes it does. Sometimes it simply allows a star to fall inward until it slips behind its own gravity. There are different kinds of black holes, at least by scale. Stellar mass black holes form from massive stars and may contain a few times the mass of the Sun, or several dozen times more. Then there are supermassive black holes, which live in the centers of galaxies and contain millions or even billions of solar masses. Between these extremes there may also be intermediate mass black holes, though they have been harder to confirm and study. The supermassive black holes are especially fascinating because they sit in places of such enormous consequence. Our own Milky Way has one at its center, Sagittarius A star, with a mass of about 4 million suns. Many other galaxies appear to host their own central black holes as well. It is one of the strange organizing facts of the universe that at the hearts of great shining cities of stars, something dark often waits. And still, it is important not to imagine these central black holes as cosmic kings issuing commands. They are part of the galactic structure, yes, but they do not single-handedly control every star in the galaxy. The Milky Way is too large for that simple picture. Our Sun orbits the galactic center because of the combined mass of the whole galaxy, including stars, gas, dust, and dark matter, not only because of the central black hole. This, again, is a soothing correction. Extreme things can exist without dominating everything. Black holes are invisible in the ordinary sense, so how do astronomers find them? Usually, they are detected by what they do to their surroundings. If a black hole has a companion star, material can be pulled from that star and spiral inward. As that matter falls toward the black hole, it forms a swirling disk called an accretion disk. The material in that disk becomes incredibly hot as it compresses and rubs together, often glowing in X-rays or other energetic light. So sometimes the darkness of a black hole reveals itself through a ring of brightness around it. This leads to one of the most beautiful paradoxes in astronomy. Some of the darkest objects in the universe are discovered because matter around them becomes among the brightest. A similar logic allowed astronomers to create the famous first image of a black hole, or more precisely, the shadow cast by one. The image of the black hole in the galaxy M87 did not show the black hole directly. It showed the bright material around it in the dark central silhouette where light could not escape in the usual way. Later, astronomers also produced an image related to Sagittarius A star, the black hole at the center of our own galaxy. These images were not simple photographs in the everyday sense. They were built through extraordinary coordination of telescopes across Earth, working together like a planet-sized instrument. There is something beautiful in that too. To glimpse one of the universe's strangest objects, human beings had to turn an entire world into part of a single observing eye. Black holes also reveal themselves through the motion of stars. If a visible star seems to orbit something unseen, and if the hidden object appears too massive and compact to be anything familiar, a black hole becomes a strong explanation. This is one of the ways astronomers inferred the presence of Sagittarius A star. By watching stars near the galactic center move in fast, tight orbits, they could calculate that an enormous amount of mass had to be concentrated there in a tiny region. So black holes are found through light, motion, heat, and geometry. They do not announce themselves directly. They leave signatures in how other things behave. And then there is time. One of the most quietly astonishing things about black holes is not just their gravity, but what that gravity does to time itself. According to general relativity, gravity is not simply a pulling force in empty space. Mass and energy curve space-time, and objects move through that curved geometry. The stronger the gravity, the deeper the curve. And in strong gravitational fields, time passes more slowly compared with regions farther away. This effect is called gravitational time dilation. Even here on Earth, time passes slightly differently depending on altitude. A clock farther from Earth's center ticks just a little faster than one at sea level. The difference is tiny, but real enough that modern systems like GPS have to account for it. Near a black hole, this effect becomes much more dramatic. If you could safely observe someone descending toward a black hole from far away, their clock would appear to slow. Their movements would seem to stretch out. Light from them would become redder and fainter. To your distant eyes, it might seem as though they never quite crossed the event horizon, but instead faded and slowed toward it. From their own point of view, however, the experience would be different. They would continue inward according to their own local time. This is the kind of idea that can make the mind feel both expanded and quiet. Time is not a universal river flowing identically everywhere. It can bend with gravity. It can stretch. It can differ from place to place. Near extreme objects, reality does not break, but our ordinary intuition does. That is often the deeper lesson of astronomy. The universe remains lawful, but not always familiar. Light itself is also bent by gravity. This is not only true near black holes, though black holes make the effect more obvious. Massive objects curve the path of light, causing a phenomenon called gravitational lensing. A galaxy or black hole between us and a distant light source can distort and magnify the background light, much as a lens might. Sometimes this produces arcs, stretched images, or multiple apparent images of the same object. So even darkness can become part of the machinery of seeing. Gravity can act like an optical instrument. When black holes feed heavily on surrounding matter, especially the supermassive ones in young or active galaxies, the result can become extraordinary. The central regions can shine with astonishing brightness, powered not by the black hole itself, but by the heated material falling around it. These active galactic nuclei, and in some especially luminous cases quasars, can outshine entire galaxies of stars. This is one of the most curious facts about black holes. The object that lets no light escape can help create some of the brightest regions in the universe, not by emitting from within its horizon, but by organizing and heating matter outside it. Quasars are especially striking because many of them lie at enormous distances. When we see them, we are often seeing the universe as it was billions of years ago. They belong to an earlier era of cosmic history, when galaxies were younger and black holes were often feeding more actively. Their light has been traveling toward us for so long that the observation itself becomes a kind of archaeology. But black holes are only one form of extreme space. There are also neutron stars, which form when massive stars collapse but do not quite become black holes. These objects are so dense that matter is compressed into astonishing states. A neutron star may contain more mass than the Sun while spanning only about 20 kilometers or so. Imagine a city-sized sphere containing the mass of a star. That is the scale of compression nature can achieve. Some neutron stars spin rapidly. Some have immensely strong magnetic fields. A few of the most intense are called magnetars. Their magnetic fields are so extreme that they belong almost in a separate category of imagination. If one of them were much closer to Earth than any known magnetar is, it could affect matter in dramatic ways. Fortunately, the known ones remain safely distant. And yet even magnetars are not signs of a broken universe. They are simply examples of how far nature can go when mass, collapse, and field strength are pushed toward extremes. There is something restful in remembering that extreme does not mean unnatural. It only means farther from daily experience. The same is true of gamma-ray bursts, among the most energetic events known. These can occur when massive stars collapse in particular ways or when compact remnants like neutron stars merge. For brief periods, they release immense energy in focused beams. If one is oriented toward Earth from close enough range, it could be significant, but such events are rare, and the universe is spacious. Most of the time, the extremes of space remain far away, part of the great background drama of the cosmos rather than a threat pressing against daily life. That is important sometimes, especially at night when the mind is more easily unsettled. The universe contains enormous energies, yes. But it also contains great distances, great intervals, and great quiet. Most extremes happen far from us, slowly or briefly, in ways that expand our understanding more than they endanger our rest. And perhaps nowhere is that more apparent than in the detection of gravitational waves. When two black holes spiral toward one another and merge, they can send ripples through spacetime itself. These ripples are called gravitational waves. Einstein predicted them long before they were directly detected. When the first confirmed signal was measured in 2015, it was one of the great scientific moments of the century. Instruments on Earth sensed an unimaginably tiny stretching and squeezing of space caused by black holes that had collided far away. Think of what that means for a moment. Human beings built instruments delicate enough to notice the echo of black holes merging across the cosmos. Not by seeing them directly with ordinary light, but by measuring how the fabric of spacetime itself trembled when the signal arrived. It is difficult to find a more elegant proof that the universe can be both violent in event and quiet in arrival. By the time those waves reached Earth, they did not come as destruction. They came as information. If these calm explorations are helping you unwind tonight, you can subscribe, leave a like, or share where you're listening from. It helps more people find this quiet place in the dark. But for now, there is nothing you need to do except breathe, and let the universe remain wide around you. As we move deeper into the idea of extreme space, a pattern begins to emerge. These objects do not only challenge our sense of size, they challenge our sense of what the universe is allowed to do. Stars can collapse into city-sized remnants. Gravity can slow time. Light can bend around invisible masses. Entire galaxies can hide dark centers. Space-time can ripple. Matter can heat to enormous brilliance while falling into darkness. And still, nothing here is outside the natural order. It is all part of one continuous universe, from the calm of moonlight on Earth to the silence around a black hole. That may be the most satisfying way to end this part. Not with fear, and not even with awe alone, but with continuity. The extreme and the familiar belong together. The same laws that let an apple fall and the moon orbit Earth also describe stars collapsing and black holes forming. The same gravity that holds you gently to your bed can, under other conditions, bend time near a collapsed star. The universe is not split into two realms, one ordinary and one impossible. There is only one universe, revealing different faces under different conditions. So as you drift towards sleep, you might imagine the cosmos not as empty darkness punctured by a few scattered lights, but as a layered world containing both gentleness and extremity. Somewhere, a black hole may be drawing matter into a hot spiral. Somewhere, a neutron star may be turning like a lighthouse. Somewhere, two compact remnants may be circling each other in a slow final dance that will one day send waves through space-time. And yet here, on Earth, the night remains quiet. The room remains still. Your breathing continues softly. The universe is allowed to be extreme without demanding that you carry its intensity. In the next part of our journey, we will move into a different kind of strangeness, away from black holes themselves and toward the deep themes of time, light, and the ancient past of the universe. We will look at why distance is also history, and how the oldest light in existence still reaches us now. But for this moment, remain here a little longer with the calm idea that even the most mysterious things in the cosmos belong to a lawful and patient whole. Black holes are not monsters. They are thresholds in nature. Neutron stars are not fantasies. They are compressed endings of stars. Gravitational waves are not magic. They are the quiet arrival of distant events written into spacetime itself. And somewhere within this immense and varied universe, on one small living planet orbiting an ordinary star, you are safe, resting, while the deeper gravity of the cosmos continues its silent work far away in the dark. Part 7: Time, Light, and the Deep Past of the Universe. Now that we have spent some time with black holes and the quiet extremes of space, it feels natural to move into something even stranger, though perhaps softer in its own way. Not deeper into gravity this time, but deeper into time. Because one of the most beautiful facts in astronomy is also one of the easiest to miss. When we look far into space, we are not only looking across distance, we are looking back into history. The universe does not show itself all at once. It reveals itself through light, and light takes time to travel. That means every star, every galaxy, every pale glow in the dark sky is telling us not only where something is, but when it was. This part of our journey is about that quiet relationship between time and light. It is about how the universe stores its past in motion. It is about why the night sky is full of old messages, why the oldest light in existence still reaches us now, and why astronomy, in a very real sense, is a form of time travel. There is something deeply calming in that thought. The universe is not rushing forward and erasing itself as it goes. It leaves traces. It carries memory and light. The past is not gone in the simple way we often imagine. It is still arriving. To begin, it helps to return to something simple. Light moves fast, faster than anything else we know, about 300,000 kilometers every second in a vacuum. In 1 second, light can circle Earth several times. In a little more than 1 second, it can travel from the Moon to Earth. In about 8 minutes, it comes from the Sun. In 4 years, it can cross from the nearest star system to us. That speed is astonishing, and yet the universe is so large that even light is often slow when measured against cosmic distances. So when you look at the Sun, you are not seeing it exactly as it is in that instant. You are seeing it as it was about 8 minutes ago. When you look at a star 10 light years away, you are seeing 10-year-old light. If you look at a galaxy whose light has taken millions of years to arrive, you are seeing that galaxy as it existed millions of years in the past. This is not metaphor. It is one of the plainest and most profound truths in astronomy. The telescope is not only a tool for magnifying distant objects. It is a machine for receiving older and older versions of the universe. And the farther out we look, the younger the universe appears. That reversal can feel strange at first. Usually, distance makes things feel older only in the sense that they have existed far away. But in cosmology, distance and age become linked through travel time. When we observe a distant galaxy, we are not seeing its present-day form. We are seeing its earlier chapter. So the remote universe becomes a record of cosmic youth. This means the sky is layered in time. Nearby stars belong to a relatively recent past. Distant galaxies belong to a much earlier one. The most remote light we can detect brings us close to the beginning. That beginning, as far as current cosmology can tell, lies about 13.8 billion years behind us. That is the approximate age of the universe. Not the age of Earth, which is much younger. Not the age of the Sun, which is also younger. But the age of the observable universe itself since the hot early state we call the Big Bang. The phrase Big Bang can sound like a loud explosion in ordinary space, but that picture is too simple. It was not like a bomb going off in some empty room. It was the early expansion of space itself, a hot dense beginning from which the universe developed. Matter, radiation, structure, stars, galaxies, planets, and eventually life all emerged later. The universe was not born finished. It began in a far simpler condition and spent billions of years becoming more structured and more complex. That is another soft lesson in cosmic history. Complexity takes time. Galaxies were not there at the start in their present form. Stars had to form. Elements had to be forged. Planets had to gather. Life had to wait. The universe had to age into the conditions that made us possible. If you could somehow go back far enough, the early universe would not resemble the sky you know. There would be no stars at first, no galaxies, no planets, only a hot, dense, expanding state, then later a dark era before the first stars began to shine. This is one of the most moving ideas in astronomy. There was a time before starlight. It is easy to forget that stars had to arrive. We live so deeply inside an already luminous universe that darkness before stars feels almost impossible to imagine. And yet there was such an era. After the early universe cooled enough for atoms to form, there followed a long stretch often called the cosmic dark ages. There was matter. There was radiation still traveling. But there were not yet stars to fill space with the kind of light we now take for granted. Then, slowly, gravity began gathering matter into denser regions. The first stars formed. The first galaxies began to assemble. Light returned in new forms. Structure deepened. The universe entered a new phase of visibility. That transition matters because it tells us the sky was not always full. It became full. The cosmos learned how to shine. And yet even before those first stars lit up, there was already an older light moving through space. We can still detect it now. This is the cosmic microwave background, often shortened to the CMB. The cosmic microwave background is sometimes called the afterglow of the early universe. It is the oldest light we can observe directly, released when the universe was only about 380 13.000 years old. That may sound ancient, and in human terms it certainly is. But compared with 13.8 billion years, it belongs to an era very near the beginning. Before that time, the universe was too hot and dense for light to travel freely in the way it does now. Photons were constantly scattered by charged particles, and the cosmos was more like a glowing fog. But as the universe expanded and cooled, electrons and nuclei combined into neutral atoms. Light could then move more freely across space. That ancient radiation has been traveling ever since. By now, because space has stretched so much during the universe's expansion, that light has been stretched too. What was once hotter, shorter wavelength radiation has become microwave light. It fills the sky almost uniformly, coming from every direction. It is not bright to our eyes, but it is there, measurable, quiet, ancient. There is something deeply peaceful about the existence of the cosmic microwave background. It means the universe still carries a faint memory of its earliest visible age. Not in words, not in symbols, in light. When astronomers map the CMB, they are not just making a picture of distant space. They are looking at a portrait of the universe when it was still extremely young. Tiny variations in that ancient glow reveal slight differences in density from place to place, the faint unevenness that would later help gravity build galaxies and larger structures. So in a very real sense, the seeds of the cosmic web were already present there, written as almost unimaginably subtle differences in the afterglow. That may be one of the most beautiful things science has discovered. The great structures of the universe, galaxies, clusters, filaments, all of them began from very slight irregularities in an early sea of matter and radiation. Vastness grew from tiny imbalances. The grand was born from the delicate. As the universe continued to expand and age, the first stars appeared. These early stars were likely different from many of the ones we see around us now. The universe at that stage had not yet been enriched by generations of stellar life and death. Heavy elements were rare. The chemistry of the cosmos was simpler. Those first stars may have been unusually massive, living fast and dying young, helping seed the universe with heavier elements for future stars and planets. So when we speak of the deep past of the universe, we are not only talking about darkness and first light. We are also talking about the first acts of stellar creation, the first furnaces where heavier elements began to form in significant amounts, the first steps toward the material richness needed for planets, oceans, geology, and life. This is why astronomy can feel so intimate even when it becomes immense. The ancient universe is not just interesting because it is old. It matters because we come from what it became. If those early stars had not formed and lived and died, the later universe would be different. So would we. All of this also changes the meaning of the night sky. A star is no longer just a point of light. A galaxy is no longer just a smudge. Everything becomes a time-marked event. Even the darkness between visible things feels fuller, because we know that the visible universe is carrying history toward us continuously. There is another word astronomers use often in this context: redshift. As the universe expands, space itself stretches. Light traveling through that expanding space also gets stretched, shifting toward longer wavelengths. For visible light, that often means shifting toward the red end of the spectrum. The greater the redshift, the more the light has been stretched, and in general, the farther and earlier the source is. By measuring redshift, astronomers can infer both distance and cosmic age in powerful ways. So redshift is not just a technical detail. It is one of the great measuring sticks of cosmic time. It helps us understand how old the light is that we receive. It helps place galaxies in the unfolding history of the universe. It helps turn the sky into chronology. In that sense, the universe is not merely visible. It is readable. If these quiet explorations are helping you unwind, you can subscribe, leave a like, or share where you're listening from tonight. It helps others find this calm little corner of the cosmos. But there is nothing you need to do right now. Just keep resting, and let the older light continue arriving. There is also something humbling in how small our own time is compared with cosmic time. Human life is brief. Even human civilization is brief. The whole written history of our species is tiny compared with the age of the Earth, and the Earth is itself younger than the Sun, and the Sun younger than the universe. Our lives unfold inside a layered nesting of timescales so large that they can feel almost merciful. They remind us that there is no need to rush the cosmos. It has always worked slowly. And yet human life, though brief, is not disconnected from that great age. We live at a particular moment in cosmic history. Not at the beginning. Not near the end. In a middle chapter of sorts, when stars still shine widely, galaxies remain visible, and the chemical richness of the universe is high enough for planets and life to form. This is not the earliest possible era, and it is certainly not the latest. There is even a kind of cosmic luck in that. Billions of years earlier, the universe would have been too young for Earth as we know it to exist. Trillions of years later, the cosmos may become far dimmer and lonelier. We live in an era where the sky is still full of evidence. The universe is old enough to have become rich, but still young enough to shine brightly. That thought can change how we feel about stargazing. We are not merely spectators at random. We are living during one of the great luminous ages of the cosmos. And astronomy lets us sense more than our own era. Because light travels with delay, we can compare different periods at once. Nearby stars show us more recent galactic life. Far galaxies show us earlier galactic life. The cosmic microwave background shows us the young universe. In a way, telescopes let the universe place its own memory side by side. That is why astronomy is sometimes described as a historical science. A geologist reads the past in rock. A paleontologist reads it in fossils. An astronomer reads it in light. The documents are not paper. They are photons. Even the phrase, looking back in time, can begin to feel gentler when you sit with it long enough. It suggests that the past is not fully lost. Not in the cosmic sense. Somewhere, the light from old events is still on the move. Somewhere, what has already happened continues its journey across space. Somewhere, ancient galaxies are still sending us their younger faces. And this includes stars that may no longer exist. A star you see tonight could, in principle, have changed or even died since the light now reaching you left it. This does not mean the sky is deceptive. It means the sky is faithful to travel time. It gives you not falsehood, but delay. That delay can feel strangely tender. The universe does not speak all at once. It speaks with distance built into its voice. There is also a philosophical softness to all of this. If light carries the past, then observation becomes a meeting across time. To look at the night sky is to enter into contact with events that do not belong entirely to your moment. It is a quiet crossing of ages. You remain here, in your room, on Earth, breathing in the present. And yet your eyes or instruments receive messages that began long before your life. Astronomy allows the present to touch the ancient. That helps explain why cosmology so often feels both scientific and emotional. It gives numbers, measurements, and models. But it also gives perspective. It shows us that our own brief existence takes place within a universe that remembers itself through light. And the future, too, is shaped by that same slow patience. Stars will continue to age. Galaxies will continue to evolve. Light from ever more distant regions will continue to stretch. The observable universe will change as time passes. Some galaxies will move beyond what future observers might easily see because of cosmic expansion. The sky of the far future will not look exactly like ours. That idea brings with it a strange tenderness. There are things visible now that may not be so easily visible in the unimaginably distant future. We live in a time when the cosmic past is still richly available. In that sense, there is a quiet privilege in being here now, in this chapter of the universe, able to look out and still see so much of what came before. Sometimes people ask whether time travel is possible. In the dramatic, science fiction sense, that remains uncertain and deeply complicated. But in the calm and lawful sense, we are already doing something like it every time we look into deep space. We are receiving the past. We are letting older moments arrive in the present. Astronomy may not let us visit the past, but it does let us witness it. That is enough to make the universe feel softer, older, and more intimate than it first appears. The stars are not only distant lights, they are delayed lights. The galaxies are not only remote structures, they are earlier structures. The cosmic microwave background is not merely radiation. It is the oldest visible memory the universe still carries. So as this part of our journey comes gently toward its close, perhaps let yourself rest with that image. The universe is a vast dark sea filled not only with objects, but with arrivals. Light crossing time. Ancient photons entering modern eyes. History moving silently through space. A cosmos that keeps its past in transit. The sun's light reaches Earth in minutes. Starlight can take years. Galactic light can take millions or billions of years. The afterglow of the young universe takes almost the whole age of the cosmos to find us. And still it comes. You are living in a universe where the past has not stopped traveling. In the next part of our journey, we will step farther outward again, away from individual ages of light and toward the largest known structures in existence, the enormous clusters, filaments, and great emptinesses that shape the cosmic web. But for now, remain here a little longer with time and light. Imagine the sky not as a flat ceiling above Earth, but as a layered archive. Nearby stars speaking in recent light. Distant galaxies speaking from early cosmic chapters. The oldest glow of all still whispering from the edge of the beginning. And here, on one small world, in one short human life, you are able to receive those whispers at all. A universe old enough to remember. Light patient enough to carry memory. And a quiet mind, resting in the dark, listening. Part 8, the largest structures in the universe and the quiet shape of everything. Now that we have followed light backward into the deep past, it feels natural to take one more step outward. Not toward a single star, or a single galaxy, or even a single era of cosmic history. This time, we are going to look at the largest patterns we know. The widest architecture of all. The places where galaxies no longer seem like the final scale, but instead begin to look like particles in something even greater. This part of our journey is about the largest structures in existence. Galaxy clusters, superclusters, cosmic filaments, vast empty voids, and the strange truth that the universe, when viewed on its grandest scales, does not look evenly filled at all. It looks more like a web, a soft glowing network stretched across unimaginable darkness. There is something especially calming about this scale, because at this level the universe no longer feels crowded with individual details. It begins to feel patterned, spacious, quiet in a different way. Galaxies become points inside larger groupings. Clusters become beads along cosmic strands. Darkness itself becomes part of the design. And perhaps that is the first thing to notice. The universe is not built as a uniform fog of matter spread equally in all directions. If it were, the large-scale view would be simpler, flatter, less textured. But it is not like that. Matter gathered unevenly. Gravity deepened some regions and left others comparatively sparse. Over immense spans of time, that unevenness grew into structure. So in this part, we will move slowly through that structure. We will begin with galaxy clusters, then drift outward to superclusters and filaments, and finally to the great cosmic voids, the enormous regions where very little seems to be. Along the way, we will feel how small the Milky Way really is, and why even the observable universe, immense as it is, still has a limit. Let us begin with something already larger than ordinary thought, the galaxy cluster. A galaxy cluster is exactly what it sounds like, though the reality is more immense than the phrase suggests. It is a group of galaxies bound together by gravity. Not just a few, but sometimes hundreds or even thousands of galaxies moving within the same larger structure. Each galaxy is itself full of stars. Each may contain hundreds of billions of them. So when we speak of a cluster, we are speaking of a gathering of stellar cities, a congregation of entire galactic worlds. And yet these galaxies are not packed together tightly in the way the word cluster might suggest in everyday life. The distances between them remain enormous. Even within a galaxy cluster, the space between galaxies is wide, dark, and difficult for the human mind to picture. But gravity works patiently across those distances. It does not need hurry. It only needs time. The Milky Way belongs to a much smaller arrangement called the local group, which is not a rich cluster in the grander sense, but rather a modest galactic family. True clusters are larger and more crowded. In some of them, the central galaxies can become immense, swollen by mergers over billions of years, surrounded by many smaller companions, all of it turning slowly inside a shared gravitational basin. There is also more in a cluster than visible galaxies alone. The space between galaxies in a cluster is not simply empty. It often contains extremely hot gas, thin but vast, glowing in X-rays. This gas is part of the cluster's total mass and history. So when astronomers study clusters, they are not only looking at the galaxies themselves. They are also tracing the matter between them, the dark matter that helps hold the whole thing together, and the wider gravitational shape of the cluster as a whole. That matters because galaxy clusters are among the largest gravitationally bound structures in the universe. A single galaxy is grand. A galaxy cluster is grandness gathered one level higher. And yet even clusters are not the final step. Clusters themselves can be part of still larger arrangements often called superclusters. These are broad regions of space where multiple clusters and groups of galaxies are associated in wider patterns. The term can sometimes be a little softer in meaning than the word cluster, because not every supercluster is tightly bound into one neat permanent object. But as a descriptive idea, it helps us feel the next rung of scale. Clusters do not sit randomly in isolation. They belong to broader territories. Our own galaxy, for example, belongs to a larger region associated with a supercluster known as Laniakea. The name means immense heaven in Hawaiian, and it suits the scale. It refers to a vast collection of galaxies and galaxy groups moving within a larger gravitational flow. Even here, though, it helps to stay calm with the terminology. These huge structures are not always like sharply outlined islands. They are more like broad cosmic landscapes, regions of influence and motion. Still, the idea matters. The Milky Way is not merely part of the local group. The local group is not merely floating by itself. It belongs to a wider context. The universe keeps widening the frame. And if we zoom out farther still, something astonishing appears. The universe on its largest scales begins to resemble a web. This is what astronomers call the cosmic web. It is one of the most beautiful large-scale discoveries in cosmology. When the distribution of galaxies is mapped across immense distances, they do not appear uniformly scattered like grains tossed evenly through space. Instead, they gather along long filaments, broad strands of matter stretching across the cosmos. Where filaments meet, clusters and superclusters can form denser nodes. Between these strands lie great emptier regions called voids. This is the web-like structure of the universe. It can be difficult to describe how strange and elegant this is. If you could somehow rise far enough above the local details and look at a great section of the cosmos, you would not see a blank darkness with galaxies sprinkled at random. You would see patterns, long luminous threads, dense intersections, and wide hollows in between. In some visualizations, it almost looks organic, like a network of veins or roots or strands of silk stretched across the dark. Of course, the universe is not literally alive in that way. The resemblance is only visual, but the emotional effect can still be powerful. The largest structures in existence look less like chaos and more like a form. So how did this happen? The beginning lies in the early universe, in the tiny differences we touched on in the last part. The young cosmos was not perfectly smooth. It contained faint variations in density, places where matter was just slightly more concentrated than elsewhere. Those variations were very small at first, but gravity magnified them over time. Regions with a little extra matter pulled in more matter. Denser places grew denser. Sparse places lost relative ground. Over billions of years, this process built the cosmic web. Dark matter plays a central role here, even though it remains invisible to us directly. We know it must exist because visible matter alone cannot explain the way galaxies rotate or clusters hold together or how structure formed as it did. Dark matter appears to have helped provide the gravitational scaffolding on which ordinary matter could gather. In a sense, the visible web of galaxies may trace an underlying web that we cannot see directly. There is something strangely beautiful in that too. The universe may owe part of its grand visible architecture to something hidden. The greatest shapes of all may rest on an invisible framework. And once again, that hiddenness does not make the universe less real. It only makes it deeper. Along the filaments of the cosmic web, galaxies are more common. Matter gathers. Clusters form at intersections, where multiple strands meet and feed more mass inward. But in the voids, matter is sparse. These cosmic voids are among the emptiest and largest known regions in the universe. Some span tens or even hundreds of millions of light years. They are not absolutely empty, but compared with the filaments and clusters, they contain far fewer galaxies. The existence of voids is one of the quietest and most unsettling facts about the large-scale universe. We often think of space as empty in the everyday sense, but cosmic voids take that emptiness to another level. They are not just spaces between stars or even between galaxies. They are regions between the great strands of structure themselves, enormous hollows in the web. And yet voids are not mistakes. They are not failures of cosmic construction. They are part of the pattern. The universe needs the emptier regions as surely as it needs the denser ones. Without voids, the web would not look the way it does. Contrast is part of structure. Emptiness helps define form. That may be one of the softest lessons of this entire scale of astronomy. Absence is not always nothing. Sometimes emptiness is what allows shape to emerge. You can think of it like music, in a way. A melody needs notes, but it also needs spacing. Silence helps sound take form. In the same way, the great architecture of the universe depends not only on clusters and filaments, but on the voids between them. The cosmic web is made of both presence and spaciousness. If these slow journeys through science help you unwind, you can subscribe, leave a like, or share where you're listening from tonight. It helps more people find this quiet place. But for now, there is nothing you need to do except keep resting while the scale of the universe widens gently around you. One of the most humbling effects of thinking at this level is what it does to the Milky Way in the mind. Earlier, the Milky Way felt immense, and it is. One galaxy, with hundreds of billions of stars, spread across roughly 100,000 light-years, is already more than enough to overwhelm imagination. But within the cosmic web, the Milky Way becomes only one galaxy inside one small group in one wider supercluster region along one set of filaments. It remains real. It remains beautiful. But its scale becomes relative again. The same thing happened when Earth ceased to be the center of everything. Then the Sun lost its central status. Then the Milky Way became one galaxy among many. And now even galaxies themselves become threads in something wider. Astronomy keeps enlarging the room around us. And still, this does not erase meaning. Smallness is not cancellation. It is context. If anything, the vastness of these structures can make our own local existence feel more tender. The Milky Way is not diminished because it belongs to something larger. It is situated. Earth is not less beautiful because it is not central. It is precious because, within these great scales, it remains the only world we know that carries our kind of life. There is also something deeply relaxing about the timescales involved here. The cosmic web did not appear in an instant. It formed gradually, through gravity acting over billions of years. Filaments grew. Clusters accumulated. Voids widened in relative emptiness. Everything about these structures speaks in the language of patience. Nothing in them is hurried. This can be easy to miss when hearing terms like largest structure or cosmic web, because the words sound dramatic. But the reality is less like a burst and more like a long settling. The universe had slight differences early on, and gravity spent billions of years quietly turning those slight differences into pattern. That means the largest structures in existence are, in a way, records of time itself. They are not only big, they are old. Their scale is tied to duration. To become this large, the universe had to continue existing long enough for structure to develop. This is one more reason why light matters so much. When astronomers observe distant clusters and filaments, they are not only mapping shape. They are also comparing earlier and later stages of cosmic structure. The farther out they look, the younger the web appears. So even the cosmic web has a history. It was not always as developed as it is now. The universe, then, is not just large. It has grown into largeness. And that brings us naturally to a boundary, or at least to a kind of horizon, the observable universe. The phrase observable universe is very important, because it reminds us that what we can see is not necessarily the whole of what exists. The observable universe includes all the regions of space from which light has had time to reach us since the beginning of cosmic expansion. Because the universe has a finite age, and because light travels at a finite speed, there is a limit to how far we can observe. That limit is not a wall. It is not the edge of existence. It is a horizon created by time and travel. This is one of the most subtle and profound ideas in cosmology. The observable universe is not the universe in the absolute sense. It is the part that has been able to communicate with us through light so far. Beyond that, there may be more universe, perhaps vastly more, perhaps even infinitely more. But light from those regions has not reached us, and may never do so depending on the expansion of space. So there is a softness to the limit. It is not an ending. It is an observational boundary. And because space has expanded while light traveled, the radius of the observable universe is larger than simple intuition might first suggest. The oldest light we receive has been traveling for almost the whole age of the universe, but the regions that emitted it are now much farther away than a naive multiplication of age by light speed might imply. This is why cosmology often speaks of the observable universe as spanning about 93 billion light-years across. The number sounds impossible, and in ordinary terms it is. But it comes from expansion, from the stretching of space during the journey. There is something almost gentle in the idea that even our largest cosmic view is partial. We do not stand in a place of complete knowledge. We stand in one location, inside one galaxy, inside one region of a web, receiving whatever light has had time to arrive. There is humility in that. The universe is allowed to exceed us. And that is not a failure. It is part of its beauty. Sometimes people feel uneasy when they hear about limits like this. But there can also be peace in it. Not everything has to be fully seen to be real. Not everything has to be fully measured to be meaningful. The observable universe is already so large that no ordinary mind can hold it comfortably. And still, beyond it, possibility remains. There is a quiet elegance to a cosmos that keeps part of itself beyond our horizon. If you imagine the universe at this largest scale, try not to imagine it as a textbook diagram. Imagine instead a vast darkness with long soft strands of galaxies gathered into filaments, brighter knots where clusters sit, and huge hollow spaces between them. Imagine our own Milky Way somewhere within one of those strands, small and local and bright with its own stars. Imagine the local group as a tiny neighborhood in that broader web. Imagine the observable universe as only the portion of this grand architecture whose light has reached us so far. And then let the idea settle that this structure was not arranged for us, and yet we are able to notice it. That may be one of the most moving facts of all. Matter became stars. Stars made elements. Elements formed planets. On one of those planets, life appeared. And eventually, in one small species, consciousness became patient enough to ask how large everything is. The universe grew a way to map its own vastness from within. That makes the cosmic web feel different somehow. Less like a cold external machine, and more like the larger setting in which awareness briefly opened its eyes. And still, for all its size, the large-scale universe remains quiet. Filaments do not rush. Clusters do not shout. Voids do not threaten. They simply exist, stretched across incomprehensible distances, moving on timescales far beyond ordinary fear. The largest things in the universe are, in a strange way, some of the calmest. That may be the most restful feeling to take from this part. Not only that the cosmos is large, but that its largeness is patient. The web does not hurry to become itself. The void does not mind being empty. The cluster takes billions of years to gather. The horizon remains where light and time allow it to be. Everything at this scale is slow. So as this part of our journey comes gently toward its close, perhaps let your thoughts widen one more time. Beyond stars. Beyond galaxies. Beyond even superclusters, to the web itself. A universe not evenly filled, but shaped. Not chaotic in the largest sense, but textured. Bright strands crossing dark openness. Vastness arranged into form. Emptiness helping define the whole. In the next part of our journey, we will move from these largest structures back toward a more intimate question: life, habitability, and the rare calm conditions that make worlds like Earth possible. After all this scale, we will come back to possibility, to planets, to why some places might allow life and many others do not. But for now, remain here a little longer in the cosmic web. Galaxies strung like quiet lanterns along enormous filaments. Great clusters glowing at intersections. Voids opening like dark seas between them. The Milky Way small within it all, and Earth smaller still. And yet here you are, resting safely on one living planet, while the largest structures in existence continue their slow, silent shape across the dark. Part 9, Life, Habitability, and the Rare Calm of Living Worlds. Now that we have drifted through the largest structures in the universe, through filaments of galaxies and the quiet emptiness of cosmic voids, it feels natural to return to something a little more intimate. Not small, exactly. Just closer to the question that matters most to us. Because after all the scale, after all the darkness and light in ancient history, there is one thought that rises gently through all of it. Why does life happen at all? Why should a universe so vast, so old, and so often so harsh contain even one small world where oceans move, air can be breathed, and living minds can wonder about the stars? This part of our journey is about that question. It is about habitability, the quiet set of conditions that might allow life to exist. It is about why liquid water matters, why stability matters, why Earth may be unusual in ways both ordinary and profound. It is also about exoplanets, the distant worlds orbiting other stars, and the long scientific search to understand whether life might exist elsewhere. There is something especially soothing about this part of astronomy, because it brings the grand back into contact with the familiar. After speaking of galaxies and the cosmic web, we return to something gentle and local in feeling. Air, water, temperature, day and night. The kinds of things that make a world not merely present, but livable. And perhaps that is the first thing to notice. A planet can exist without being habitable. In fact, most worlds we know are not gentle places for life as we understand it. The universe seems very good at making planets, but not every planet becomes a place where rivers can flow, climates can stabilize, and chemistry can patiently grow into biology. That is important, because people sometimes imagine habitable worlds as though the universe were full of easy copies of Earth, waiting in every direction. Perhaps such worlds are common. Perhaps they are rare. We do not yet know. But what we do know is that being a planet is not enough. A world needs more than existence. It needs balance. Earth teaches that lesson quietly. At first glance, Earth can feel ordinary to us simply because it is home. Air is normal because we breathe it. Water is normal because we drink it. The blue sky, the turning seasons, the warmth of the sun, the pressure of gravity, all of these seem so familiar that they disappear into the background of daily life. But if we imagine Earth from a little distance, not emotionally but astronomically, it begins to look much stranger. It is a rocky planet with a long-lasting atmosphere, abundant liquid water on the surface, moderate temperatures across large regions, active geology, a magnetic field, and long-term stability under an ordinary star. That combination is not trivial. It is not automatic. It is a layered success. One of the most important ingredients in that success is liquid water. Water matters because it is an unusually versatile substance for life. It can dissolve many chemicals. It allows molecules to move, interact, and react. It stores and distributes heat in ways that help moderate climates. It expands when it freezes, which is an unusual and quietly important property. Ice floats, and because it floats, bodies of water can freeze at the surface while remaining liquid below, which protects deeper water from total solidification. On Earth, water cycles through ocean, cloud, rain, snow, river, mist, and underground flow. It is one of the great quiet movers of planetary life. So when astronomers look for potentially habitable worlds, one of the first questions they ask is whether liquid water might exist there, at least in principle. That leads naturally to the idea of the habitable zone, often nicknamed the Goldilocks zone. This is the range of distances from a star where temperatures might allow liquid water to exist on a planet's surface, assuming other conditions are suitable. Not too hot, not too cold, not too near the star, not too far. The phrase is useful, but it can also be misleading if taken too simply. A planet inside the habitable zone is not automatically habitable. Venus and Earth remind us of that. Venus lies near the inner edge of the Sun's habitable zone in some definitions, and yet its thick atmosphere has driven a runaway greenhouse effect, making it far too hot and crushing for Earth-like life. Mars, on the other hand, sits near or beyond the outer edge depending on how the zone is defined, and while it may once have had more liquid water, the modern planet is cold and dry at the surface. So the habitable zone is not a promise. It is more like an invitation, a range where the possibility becomes more reasonable, but only if other pieces also fall into place. And there are many other pieces. A world's atmosphere matters enormously. Too little atmosphere, and the surface may struggle to hold heat or shield life from harmful radiation. Too much of the wrong kind, and the greenhouse effect can become overwhelming. The composition matters too. An atmosphere is not simply a blanket. It is also a filter, a reservoir, a chemical participant, and a climate regulator. A planet's size matters as well. A world too small may lose its atmosphere more easily over time, especially if its gravity cannot hold gases well enough. A world too large may become something more like a mini Neptune, wrapped in a deep envelope of gas that changes surface conditions completely. Again and again, habitability seems to depend on middle conditions, not on extremes. Then there is the star. Not all stars are equally calm hosts for life. A star that burns steadily over very long timescales may be more helpful than one that changes rapidly or blasts its planets with intense flares. Our Sun, while not perfectly quiet, is relatively stable over the timescales that mattered for life on Earth to emerge and evolve. That kind of steadiness may be one of the most underappreciated ingredients in habitability. Life, especially complex life, may need time more than anything else. Time without too much interruption. Time for chemistry to become self-replicating systems. Time for evolution to explore countless forms. This is another reason habitability feels peaceful as a topic. It is not only about the right ingredients. It is about patient stability. Earth also benefits from having a large moon, which helps stabilize the tilt of our planet's axis over long periods. Without such stabilization, Earth's tilt might vary more chaotically, with large consequences for climate. This does not mean every habitable world needs a big moon, but it reminds us that even things we rarely think about, like the presence of a nearby satellite, may influence how calm or chaotic a world becomes. Plate tectonics may matter too. On Earth, the movement of crustal plates helps recycle carbon and other materials, influencing long-term climate regulation. Continents shift, mountains rise, oceans open and close, and carbon moves between rock, atmosphere, and sea. Over very long timescales, these processes may help prevent climate from drifting too far toward permanent freezing or permanent overheating. A living world may need geology almost as much as biology. So when we ask whether a planet can host life, we are not really asking one question. We are asking many questions at once. Is there water? Is there a suitable temperature range? Is the atmosphere helpful or hostile? Is the star stable? Can the planet hold onto air? Is there long-term climate balance? Are there useful chemicals? Has enough time passed? Is the history of the world one of calm persistence or repeated destruction? The more we learn, the more habitability begins to look less like a switch and more like a narrow corridor. Not impossibly narrow, perhaps, but narrow enough to command respect. This brings us to exoplanets, the planets orbiting stars beyond our Sun. For most of human history, other planets were known only within our own solar system. The stars looked distant and unreachable, and whether they had worlds of their own remained mostly a matter of imagination. But over the last few decades, astronomy has changed that picture dramatically. Thousands of exoplanets have now been detected, revealing that planets are not rare exceptions. They seem to be common outcomes of star formation. This was one of the great quiet revolutions in modern astronomy. The universe went from containing one known planetary system to containing many thousands. And with each new discovery, the imagination of what a planet can be expanded. Some exoplanets are hot giants orbiting very close to their stars, worlds more massive than Jupiter completing an orbit in just a few days. Some are rocky planets somewhat larger than Earth, often called super-Earths, though the name does not guarantee they are Earth-like in climate or habitability. Some orbit dim red dwarf stars. Some travel in systems with multiple planets packed close together. Some may be ocean worlds. Some may be scorched. Some may be frozen. Some may be stranger than our current categories can comfortably describe. The methods used to find them are themselves beautiful in their subtlety. Often astronomers do not see the planet directly. Instead, they notice a small dimming when a planet passes in front of its star, or a tiny gravitational wobble in the star caused by the planet's pull. It is a quiet science of slight changes. A star dips in brightness by a very small amount, over and over, and from that rhythm a hidden world is inferred. There is something lovely in that. Whole planets discovered by patience. And among these many exoplanets, some lie in the habitable zones of their stars. That does not mean they are inhabited, or even truly habitable, but it makes them especially interesting. These are the worlds that keep the question open. Could life be common in the universe? It is possible. Could life be rare? That, too, is possible. At the moment, the honest answer is that we do not know. We know that the ingredients for planets are widespread. We know that water exists in many forms across the cosmos. We know that organic molecules are not unique to Earth. We know that planets exist in great numbers. But the transition from chemistry to life remains one of the most profound unknowns in science. And even if simple life is common, complex life may be much rarer. Intelligence rarer still. The steps from a stable world to self-aware beings may involve long chains of contingency, narrow escapes, and unusual transitions. Earth offers one successful example, but a sample size of one is small. There is a phrase people sometimes use in this context: Earth may be special, though not necessarily unique. That is a calm way of holding the mystery. We do not need to assume Earth is the only living world. We also do not need to pretend that living worlds must be everywhere. The wise position, at least for now, is one of open wonder. One way astronomers hope to learn more is by studying exoplanet atmospheres. If a planet passes in front of its star, a tiny portion of starlight may filter through the planet's atmosphere before reaching us. By analyzing that light, scientists can sometimes infer the presence of certain gases. In the future, if not already in limited ways for some larger worlds, this may allow us to search for possible biosignatures, atmospheric clues that could hint at life, such as combinations of gases that are difficult to maintain without biological processes. But even here, caution matters. A gas that looks promising may have non-living explanations. A living world may not advertise itself clearly. The search is subtle. The universe is not obliged to answer quickly. And maybe that is appropriate. The question is so large that perhaps it deserves a patient method. If these quiet explorations help you drift towards sleep, you can subscribe, leave a like, or share where you're listening from tonight. It helps this calm corner of the cosmos reach more people. But for now, there is nothing you need to do. Just listen, and let the thought of living worlds remain gentle. There is another side to habitability that matters too, and it is less about distant planets than about our relationship with Earth. The more we learn about how many conditions may be needed for a world like ours, the more Earth begins to feel not less ordinary, but more precious. A breathable atmosphere, surface oceans, long-term stability, life persistent for billions of years, complex ecosystems. A climate that, though changeable, stayed within certain life-permitting bounds long enough for forests, animals, and human beings to appear. All of that may be the result of many converging factors. This does not mean Earth is magically protected or cosmically guaranteed. Quite the opposite. It means a habitable world may be a delicate achievement, one worth understanding and caring for. Astronomy can make us feel small, but it can also make us protective. When you realize how many worlds are hostile, the kindness of this one begins to stand out more clearly. A rocky surface beneath you instead of toxic clouds. Rain instead of acid mist. Breathable air instead of crushing gas. Oceans instead of sterile dryness. A star stable enough to support long biological time. These things are not trivial. And there is also a philosophical quietness in the idea of habitability. A habitable world is not defined by brilliance or grandeur. It is defined by moderation, by balanced temperature, by persistent water, by chemical opportunity, by time. Life does not seem to require the most extreme places. It requires the calmer ones. The places where conditions remain open long enough for fragile processes to continue. That makes habitability feel less like a conquest and more like hospitality. A world does not need to dazzle the universe. It only needs to remain gentle enough for life to stay. Perhaps that is one reason Earth feels so moving when seen from afar. Not because it is the biggest or brightest thing in space, but because it is blue, temperate, and alive. A small place of long permission. And if there are other living worlds, perhaps they too are worlds of moderation. Perhaps they are quiet places orbiting quiet stars, with weather, seas, seasons, or equivalents stranger than ours. Perhaps they are not spectacular from a distance. Perhaps they are simply stable. Perhaps life, across the cosmos, prefers the patient middle. That is a comforting possibility. It is also possible that many planets drift near the edge of habitability, neither clearly dead nor fully alive, worlds where life could almost happen, or happened briefly, or remains hidden beneath ice or underground oceans. Our own solar system may contain such places. Europa and Enceladus, with their subsurface oceans, are reminders that liquid water need not always lie openly beneath the sky. Habitability may sometimes hide below frozen shells, far from sunlight, in internal warmth and chemical gradients. This expands the imagination in an important way. A living world need not always look like Earth. There may be many forms of planetary kindness, many ways for a world to make space for complexity. Some may be familiar. Others may be cold, dark, and sealed. And yet, for us, Earth remains the touchstone. The only known world where life has certainly taken hold and become complex enough to ask whether it exists elsewhere. There is something almost tender in that loneliness. Not a tragic loneliness, necessarily. Just a real one. We may not be alone. But until we know otherwise, Earth stands as the only confirmed living world in all our observations. That does not diminish the rest of the universe. It deepens the significance of this planet. It also changes how we might think about the phrase, ordinary life. Life may not be ordinary at all. It may be one of the rarest and calmest outcomes of cosmic history. So as this part of our journey begins to settle toward its close, perhaps let yourself hold both possibilities at once. The universe may be full of worlds where life could emerge. The universe may also be one where living worlds are precious and uncommon. We do not yet know. But we do know enough to say this: habitability is subtle. Life depends on balance. Earth is not just a planet. It is a successful world. That success rests on many things. The right distance from the sun, the right kind of atmosphere, long-lived water, geological and chemical cycles, time enough for evolution, a star calm enough to allow patience, and perhaps a measure of luck woven through the whole story. In the next part of our journey, we will move from habitability to the far future, toward the long, slow fate of the universe itself, where stars fade, galaxies change, and time stretches beyond easy imagination. But for now, remain here for a little while with the calm thought of living worlds. Imagine them scattered through the dark, some perhaps barren and silent, some perhaps stormy and impossible, some perhaps frozen, some perhaps hidden under ice. And somewhere, maybe many places, maybe only a few, worlds with the rare calm of water, air, chemistry, and time. Worlds where something fragile began and kept going. And among them, certainly, this one, Earth. A small blue world, not the largest, not the brightest, not the center of anything, and yet gentle enough for oceans, forests, breath, memory, sleep, and wonder. A planet quiet enough for life. A universe wide enough to make that feel miraculous. Part 10. The slow future of the universe. And now, after drifting through stars, galaxies, black holes, light, time, and the rare calm of living worlds, we arrive at the quietest question of all. What happens next? Not tomorrow. Not next year. Not even in the next million years. We are going to think much more slowly than that. We are going to let the imagination stretch far beyond ordinary history, beyond human civilization, beyond Earth as we know it, beyond the Sun, beyond the Milky Way in its present shape, and even beyond the age of stars themselves. This final part of our journey is about the future of the universe. That phrase can sound dramatic at first, almost heavy, as if it must lead somewhere cold or frightening. But the truth is gentler than the imagination often expects. The future of the universe is not one single event. It is not a final curtain dropping all at once. It is a long unfolding, a slow thinning, a gradual dimming across timescales so vast that they no longer feel like countdowns. They feel more like weather in eternity. There is something deeply restful in that. The universe does not rush toward its future. it drifts into it. And so in this last part, we will move slowly through that drift. We will begin close to home, with the future of Earth and the Sun. Then we will widen outward to the future of the Milky Way, the coming encounter with Andromeda, the gradual slowing of star formation, the continued expansion of space, and the astonishingly distant eras when the universe may become darker, quieter, and more spread out than anything we know now. It is a very long story. And like many very long stories, it softens when heard at the right pace. Let us begin with the most familiar star in our sky. The Sun, which can feel so constant in daily life, is not eternal. It is stable on human timescales, yes, more than stable. Faithful, almost beyond description. It has been rising over Earth for all of recorded history and long before. It has warmed oceans, lit forests, fed ecosystems, and marked the rhythm of day and season. But like all stars, it has a life cycle. Right now, the Sun is in the long middle phase of its existence, steadily fusing hydrogen into helium in its core. This stage lasts for billions of years, which is why it can feel practically permanent to creatures as brief as we are. But eventually, the hydrogen in the core will become depleted enough that the Sun's balance will begin to shift. That moment is unimaginably far in the future from our perspective, about 5 billion years or so. And even then, the change will not be sudden. The Sun will not wake one morning in a new form. It will age slowly, as stars do, through processes measured in millions and billions of years. As the Sun changes, its brightness will gradually increase. Long before it becomes a red giant, Earth's conditions will likely become much harsher. Oceans may begin to evaporate. Climate systems will be transformed. The familiar Earth, with open seas, moving weather, and abundant life, belongs to a temporary window in solar history, not an eternal one. There is sadness in that, perhaps, but also perspective. The kindness of Earth was always part of a long, temporary balance, not a cosmic guarantee. A chapter. Much later, the Sun will expand into its red giant phase. Its outer layers will swell enormously. Mercury will almost certainly be lost. Venus too. The fate of Earth is less certain in some details, but no matter the exact path, the world we know will not survive unchanged. The inner solar system will be transformed by the changing star at its center. And yet even this is not violence in the ordinary sense. It is not like an explosion in a human story. It is more like a lamp slowly flaring larger as its internal balance changes, until the rooms around it are no longer what they once were. Eventually, the Sun will shed its outer layers, creating a glowing shell of gas around its remnant core. What remains will become a white dwarf, a small dense ember of a star, no longer powered by the same kind of active fusion. Over vast spans of time, it will cool and fade. So the future of our Sun is not an abrupt extinction. It is a long transformation from steady star to swollen giant to cooling remnant. There is something peaceful in knowing that even endings in the cosmos often happen by degrees. By the time the Sun becomes a white dwarf, the Earth as we know it will be gone. But the wider universe will still be full of stars. The galaxy will still turn. Other worlds may still orbit other suns. Our own local story ends, but the larger story keeps going. This is one of the most important emotional lessons astronomy offers. The end of one familiar world is not the end of everything. The universe is always wider than the place we call home. And the Milky Way, too, has its own future. As we touched on earlier, our galaxy and the Andromeda galaxy are moving toward one another. This process is already underway, though on a scale so slow that already barely feels like the right word. In around 4 to 5 billion years, the two galaxies will begin their long interaction. Their shapes will distort. Their spiral structures will stretch and warp. Over time, they will pass through one another and eventually merge into a larger single galaxy. This can sound catastrophic, but only if we imagine it too quickly. On the scale of individual stars, Actual collisions are very unlikely, because the distances between stars are so immense. Instead, what happens is a great gravitational reshaping. Stars are drawn into new orbits. Gas clouds are compressed. New waves of star formation may flare up in some regions. Tidal streams of stars and matter may arc far out into space. It is a galactic dance, not a crash in the human sense. And if Earth or anything like Earth were still around to see that sky, it would be astonishing. The night would no longer hold Andromeda as a faint distant smear. It would grow larger and brighter across the heavens over immense spans of time. The familiar shape of the Milky Way would slowly be joined, then transformed, by the presence of another galaxy drawing near. Imagine a future sky where the stars are still there, but the great background glow has changed. A new vast luminous structure rising across the darkness. Not because something violent happened overnight, but because galaxies kept moving for billions of years. Eventually, the Milky Way and Andromeda may settle into a large elliptical or lenticular remnant, sometimes informally nicknamed Milkomeda. The name is light-hearted, but the process behind it is grand. Our local group of galaxies will become simpler in one sense, with the two largest members now fused into one wider system. And beyond the local group, the rest of the universe continues to expand. This is one of the deepest truths in modern cosmology. Space itself is stretching. Galaxies that are not gravitationally bound to us tend, on the largest scales, to recede from one another as the universe expands. This expansion was discovered through the redshift of distant galaxies, and later it became clear that the expansion is not merely continuing, it is accelerating. The cause of that acceleration is still one of the great mysteries in science, and it is often given the name dark energy. The phrase does not mean we fully understand what it is. It is more like a placeholder for the observed fact that the large-scale expansion of the universe is speeding up in a certain way. Dark energy is one of those scientific ideas that sounds dramatic but behaves quietly. It does not tear apart your room. It does not pull on your body in any noticeable way. Its significance emerges only on vast cosmic scales, where galaxies are separated by immense distances and expansion has room to matter. Over long enough times, this means that galaxies beyond our local gravitationally bound region will drift farther and farther away. Their light will become more stretched, fainter, and harder to detect. In the remote future, if dark energy continues to act in the way current observations suggest, distant galaxies may recede beyond the reach of future observation. This leads to one of the strangest and saddest thoughts in cosmology. There may come a time, far beyond human timescales, when observers in our galactic remnant would no longer easily see the wider universe. The local group, or what remains of it after mergers, would stay gravitationally bound. But the more distant galaxies could slip beyond the observable horizon, their light stretched away by the expansion of space. In that future, the sky might appear lonelier than it does now. Not because the universe contains less beyond the local galaxy, but because the evidence of that wider cosmos would no longer reach those future observers in the same way. We live in a time when the universe is still richly visible. That is easy to overlook. But it is one of the quiet privileges of our cosmic era. The wider galaxy population is still observable. The cosmic microwave background is still detectable. The universe still reveals much of its own history. Future beings, if any exist in unimaginably distant ages, might inhabit a cosmos that appears smaller and more self-contained simply because the larger evidence has drifted away from view. There is tenderness in that thought. The universe does not remain equally knowable in every age. But even before that lonely horizon becomes important, another longer process has been underway from the beginning. The rate of star formation in the universe is not constant. It was once much higher than it is now. The cosmos was more fertile in its younger ages. Gas was more abundant and more easily gathered into new stars. Galaxies were more active. Quasars were more common. Starbirth was, in a sense, more frequent. Today, new stars still form, of course. Nebulae still glow. Gas clouds still collapse. But over the largest scales, the universe has already passed its busiest age of star formation. It is gradually becoming less productive in that sense. The great bright rush of youth is behind it. This does not mean stars are about to disappear. Far from it. Existing stars will continue to shine for vast spans of time, and many long-lived red dwarfs may burn for trillions of years. But the overall pattern is one of decline. The raw cold gas needed to form entirely new generations of stars becomes less available over time, locked into stars, planets, remnants, or heated so that collapse becomes less easy. So the universe is not only expanding, it is also, very gradually, using up its easier opportunities for new starlight. This leads us into a future where stars still exist, but fewer new ones are born. Galaxies age. Bright blue stars become rarer. Long-lived red dwarfs dominate more and more. The night sky of the remote future may not be full of the same variety of stellar youth that we see now. It may be calmer, dimmer, and older in temperament. Eventually, on timescales so large they barely resemble time in any human sense, the era of normal star formation may come mostly to an end. The universe would then enter a much darker chapter, still not empty, still not finished, but change. Some stars would remain. White dwarfs would cool. Neutron stars would persist. Black holes would continue to wait in darkness. The long-burning red dwarfs would shine on, outliving almost everything familiar to us now. But the bright age of many fresh stars would fade. This phase is sometimes described in terms of cosmic eras. First comes the era in which stars dominate. Much later, there may be a degenerate era, populated by stellar remnants, cooling embers, collapsed objects, and the sparse leftovers of former brilliance. Beyond that, still stranger futures have been imagined by physicists, depending on how far the known laws continue to apply. Black holes themselves, which can seem like permanent wells of darkness, may not be truly eternal either. According to an idea associated with Stephen Hawking, black holes can very slowly lose energy through a quantum process now called Hawking radiation. The effect is fantastically small for large black holes. A stellar black hole would take an inconceivably long time to evaporate. Supermassive black holes, much longer still. These timescales are so extreme that even saying them aloud does not really help the mind. Trillions of years are not enough. One must move far, far beyond that, to numbers that leave ordinary intuition behind completely. But in principle, even black holes may not last forever. And if that is true, then the universe's future quiet becomes quieter still. Eventually, if expansion continues and usable energy differences become ever more scarce, the cosmos may drift toward what is often called heat death. The phrase sounds violent, but it is really the opposite. It does not mean heat in the everyday sense of fire or fever. It means a final state of maximum entropy, a condition in which energy is spread so evenly that no large organized processes can easily occur. No bright stars being born. No great temperature differences to drive new structure in the familiar ways. Just a thinner, darker, quieter universe. This is perhaps the ultimate future imagined by current cosmology, though it remains a model built from what we know now, not a witnessed fact. And even here, it is important not to imagine a dramatic ending. Heat death is not a cosmic scream. It is a fading. A gradual settling into stillness across timescales so vast that, eventually, becomes almost meaningless. And perhaps that is why it can be heard gently. The universe is not rushing toward doom. It is relaxing into greater thinness and quiet. There are other speculative possibilities too. Some cosmological models have imagined different endings depending on the behavior of dark energy or other unknown physics. Perhaps the far future contains surprises. Perhaps the laws we know are only part of the story. Science, when honest, leaves room for that uncertainty. But among the currently favored large-scale pictures, the universe's future is not one of sudden collapse. It is more often imagined as a long continuation of expansion and dimming. That is a future of patience. If these calm explorations have helped you drift tonight, you can subscribe, leave a like, or share where you're listening from. It helps others find this quiet place in the dark. But for now, you do not need to do anything at all. Just keep listening, and let time stretch until it softens. One of the most moving things about the far future of the universe is what it does to our sense of the present. When you realize that stars will burn for trillions of years, that galaxies will merge over billions, that black holes may outlast almost everything, and that even those black holes may one day fade, the present becomes neither trivial nor crushing. It becomes delicate. We live in a bright era. That may be the simplest way to say it. The stars are numerous. Galaxies are visible. The cosmic background still speaks. New stars still form. Planets exist. Life exists. The universe has already become rich, but has not yet thinned into its lonelier chapters. We are not at the beginning, and we are certainly not near the end. We are in one of the luminous middle ages of the cosmos. That gives the night sky a special kind of tenderness. The stars above you are not merely objects. They are part of a temporary abundance. The Milky Way, bright with many stars, belongs to an era that will not last forever. The same is true of Earth's mildness, the sun's stability, and the visibility of the wider universe. But temporary does not mean lesser. In some ways, it means more precious. The universe's great lesson may not be that everything fades and therefore nothing matters. It may be that everything changes, and therefore every calm chapter has its own beauty. Earth has its chapter. The sun has its chapter. The Milky Way has its chapter. The universe itself has chapters. Some are bright. Some are dense. Some are still to come. Ours happens to be one in which stars shine widely, galaxies still speak clearly across space, and a living planet can lie under the sky and wonder about all of it. That is enough to make the present feel gentle. So as this final part of our journey begins to close, perhaps let yourself imagine the future not as a threat approaching, but as a series of widening silences. First, the Earth changing under the slow aging of the sun, then the sun becoming a giant, then a white dwarf. The Milky Way meeting Andromeda and settling into a new form. Distant galaxies receding as space continues to expand. Fewer new stars being born. Old stars lingering. Red dwarfs outlasting almost everything familiar. Black holes remaining in the dark. And far beyond even that, a universe stretched thin, quiet beyond ordinary comprehension. Not an ending with a crash. An ending with a whisper. And still, here you are now, in the bright middle chapter, on a small blue world under an ordinary star, resting in a room that belongs to the warm age of the universe. That is where this whole journey has been leading, in a way. Not just to distant knowledge, but back to the calm fact of being here in this particular era at all. The stars are still on. The galaxies are still visible. The universe is still telling its story in light. And you are alive inside one of its most habitable and luminous moments. That may be enough for tonight. So let the future be far away now. Let the red giants and white dwarfs and merging galaxies remain where they belong, in the immense distances of cosmic time. Let the dark energy keep stretching space without asking anything of you. Let the black holes wait in their patient silence. Let the far future cool in peace. You do not need to carry the age of the universe to sleep. You only need this moment, this breath, this bed, this small living world turning in the dark beneath a sky still full of stars. And if your mind is ready now, let the words grow lighter. Let them become only sound. Let the future drift away, the past settles softly behind you, and the whole vast universe continue its slow, quiet unfolding without effort. The cosmos will keep moving whether you watch it or not. The galaxies will keep turning. The stars will keep burning, light will keep traveling, time will keep opening, and you can rest deeply, quietly, here, in the brief bright age of the universe.